work on gravitational wave observables for inspiral compact binaries from Post-Minkowskian scattering data.
Thank you. I'm sorry for the long title.
It's pretty long. Go ahead, Rafael, please.
Okay, thank you. Yes, I'm going to talk about gravitational wave observables for inspirally compact objects, and how we can use Post-Minkowskian scattering data to learn about the binary problem. So this is work in collaboration with a bunch of young postdocs, active people that I hope they're in the audience, and they can also answer many questions. Giyuk Cho, Christoph Lapa, Gregor Kalin, Senwen Liu, and Xijin Yan. So let's get started. So I have decided to split my talk in two parts. So in the first part, I'm going to tell you about what I like to call the boundary-to-bound dictionary, namely this idea to connect information or gauge invariant observables from scattering data to compute gauge invariant observables for binary system, for bound states. And in the second part, I'll tell you about this effective field theory approach that we have extended from post-Newtonian that you have heard over the last many years that we have worked on post-Newtonian sources. We have extended these effective field theory ideas to the post-Minkowskian regime to study the scattering problem to compute observables and then input into this boundary-to-bound dictionary that would allow us to compute gravitational wave observables for binary systems. So very good. So let's get started. So I guess I don't have to motivate the two-body problem to this audience. That's the theme of this conference. We also had a beautiful tutorial by Julio and a great talk by Spi, who described how one way in which we can use scattering data, in particular the scattering amplitude, to compute observables. I can hear somebody talking. No, okay. To compute observables from post-Minkowskian scattering data, in this case from scattering amplitudes for binary systems in the classical limit. As Julio and Spi explained, this idea goes back to a very nice work by Cliff Chan, Ira Rostin, and Michael Solon, who confronted with this problem to connect the scattering amplitude in the classical limit to compute observables for binary systems. They decided to match into an effective theory. Ira's an effective field theory, so it's okay, let's construct an effective theory from which we can extract the Hamiltonian or the potential. And once we have the potential, the Hamiltonians, is gravity is universal. While you have this, this object, we can compute the equation of motion and get any observable that we want. For example, the scattering angle, the periastrum advance, and so on. And as we see here, this is, for example, the 3 p.m. Hamiltonian at order GQ that was computed in 2018 by Spi and collaborators. Now, there is absolutely nothing wrong with this. This is perfectly fine. But in the spirit of on-shell objects of this whole amplitudes program, you might ask yourself, because we are trying to compute a gauge invariant observable, such as the periastrum advance, for example, for binary system, and we start with a gauge invariant observable, such as the scattering amplitude, is there a way to connect the two without having to go through this matching, without having to go through this potential? And the answer is yes, we can. And this is the origin of this boundary-to-bound dictionary. So the question is, do we need the Hamiltonian? The answer is no. We actually do not need the Hamiltonian to compute gauge invariant information for binary systems. And this is in the first part of my talk, what I'm going to tell you about. I have already covered a little bit of this for the conservative sector. And now, hopefully, I'll tell you a little bit more about how we can connect also gravitational wave observables, also the radiation sector that seems to be the next frontier for us in post-Minkowskian studies. So very good. So I think when people enter, they are not muted automatically, so I can hear an echo right away. So if the organizers can mute people that enter, that would be great. Thank you. So, okay, so how this story started? So this started with the work that I did in collaboration with Gregor Kalin. And what we did was noticing something that was already sitting there in the first paper by SB and collaborators, and particularly when they computed the scattering amplitude, they realized that if you look at the, they didn't write it this way, but if you look at the scattering amplitude and you Fourier transform with respect to the relative momentum, the transfer momentum, sorry, and then you go into this coordinate R, which in a sense is fixed in a gauge, what is called an isotropic gauge, the coefficients of the scattering amplitude are directly connected to the coefficients of the central mass momentum, or the p square, something that some people call like the on-shell. It's an object that appears also in the effective one-body approach, and something that I like to call the impetus formula. Now, as you heard also from Julio, there's a particular way to do this because there is this y basis that you can choose, because there are divergences in this object that you need to subtract. So there's an IR finite piece that you need to take. But once you take those considerations into account, they realized, or they made this observation, that those two things were the same. And it looked just as a curiosity in the paper, but to me, when I looked at it, it was my first, not eureka moment, but this is funny moment, like what Asimov said, because this looks like this should be generic, they should be true to all order, and this is something that we could use right away to extract physical information rather than going through the Hamiltonian. And lo and behold, together with Gregory, we show that indeed, this is true to all orders, that this connection between the center of mass momentum and the scattering amplitude Fourier transform, it is indeed valid to all post-Minkowskian orders once you subtract away these infinite pieces in this so-called Y basis, and you only deal with the potential part, just the local potential part, which I will explain a little bit more as we move along. So once we have this direct connection between the scattering amplitude, the potential local part of the scattering amplitude by Fourier transform to all orders in the post-Minkowskian expansion, then we can do a lot to directly relate the scattering amplitude to physical information, for example, to compute the scattering angle. I haven't gone yet to the bound case, but just to go to the scattering angle, we don't need to go through the Hamiltonian. There is something very pretty. This problem was solved many years ago in the 50s by this guy, Firsov, who realized that you can invert the relationship that I'll show you in a second between the scattering angle and the center of mass momentum, which means that once you're given the center of mass momentum, you can get the scattering angle and vice versa. And if you do a post-Minkowskian expansion, the coefficients of the expansion of the angle and the coefficients of the expansion of the center of mass momentum, which in this case is just made dimensionless, so we can connect dimensionless objects, are directly related. This is a very easy to write down formula at any order. The old order formulas are more intricate, and Gregory found them, and it's actually quite simple. And therefore, if you know the coefficients of the momentum through the amplitude, you can get the scattering angle right away, and we don't have to go through the Hamiltonian. And this is actually a much nicer package of the exact same thing, which is essentially how Firsov solved this problem, how he inverted the problem, is going through the so-called radial action that we have heard also in many various talks. Also in the talk by Svi, at the very end, he also mentioned that he can repackage some of this information in the form of the radial action. So what is the radial action? This object that Julio also described at the very end of his tutorial is the integral of this radial momentum. And in this case, for the case of the scattering, we're integrating between in time, if you want, between minus infinity and plus infinity, but in position, when we do this integral in the radial momentum, we're going from the minimum. Actually, this is twice, so eventually you come from infinity to infinity, but you can rewrite this as twice the integral between half the world, so half the world length, so basically between r min and infinity. And this integral of PR, which we can extract directly from the amplitude, give us the radial action. Now, once you know the radial action, you take a derivative of the radial action with respect to the angular momentum, you can extract the scattering angle. And because we have this connection, this so-called impetus formula between the center of mass momentum and the Fourier transform of the amplitude, the IR finite piece, we can directly then map the scattering angle to the scattering amplitude without having to go through the Hamiltonian. So this is not that surprising. Everything has been done in the unbound case. This is for positive binding energy. But what is remarkable is that this radial action, or if you want, this impetus formula, which relates the scattering amplitude now Fourier transform, so basically we're writing a local expansion for this center of mass momentum, is essentially universal as well. Like the Hamiltonian, this p squared is universal, which means we can use it for any type of situation. In particular, we can use it for the bound case. So instead of doing a continuation of the Hamiltonian, so to speak, by solving the Hamiltonian equations with negative binding energy, here we can do exactly the same thing with the radial action and solve for the radial action for the bound problem by then analytically continue the center of mass momentum for negative binding energies. And what happens, the changes with respect to the unbound case is that now the computation of the radial action is essentially the same, except that now the zeros of the radial momentum, the problem is bound. So there are two zeros, which are r minus and r plus. So the integral that you have to do is between the zeros of this object, which goes between r plus and r minus. But there are various tricks that we can implement to actually do this integral. So we can compute the momentum from the amplitude, plug it in here, and do the integral, and analytically continue to negative binding energies. We will compute the radial action, now the object, the gauge barrier object from which we can compute all the gravitational observables directly from the scattering amplitude without having to pass through the Hamiltonian. If we vary the radial action with respect to the angular momentum, we get the periastrum advance. If you vary with respect to the energy, in the other case, in the case of the outbound orbits, we get the time delay. Here we get the radial period, and we can also get this redshift function if you vary with respect to the masses. I'm not going to get into this. This will be the two important objects for us. So this is great. This means that you give me the scattering amplitude, and I can directly construct this radial action. In fact, we don't even, for this calculation, we don't even need to know what R plus and R minus are. There's a beautiful trick that was implemented, I think, by Sommerfeld, in which you deform the contours because they are the zeros of this function. So you can actually deform the contours to infinity. So you can actually do this to all orders. And Gregor found the solution to all orders, and it's in terms of some hypergeometric functions. So you can actually get the direct connection between the coefficient of the scattering amplitude and all the observables that you want just by doing this integral of the radial action. However, you might ask yourself, you might pause for a second and ask yourself, well, that's great. We have the scattering amplitude related directly to all the observables through the radial action, but we don't measure the scattering amplitude. We measure the scattering angle, say. So what happens if I rewrite this radial action in terms of the actual observable, which could be, in the case of the conservative sector, the scattering angle. And then when you start doing that, then you realize that if you write, for example, the scattering angle, which was the derivative of the radial action for the unbound case, so it would be this integral here, that would be the derivative of the radial momentum with respect to J, so this is what you get. And the zeros are now between infinity with the unbound case and the closest approach. And the bound case, you get a derivative, it gives you the periastrum advance. So the points are different. These are the R plus and R minus of the bound orbit, but the object is exactly the same, which means that when you go ahead and do these integrals and you expand, then you realize, and this was our second, that funny moment, is that the coefficients of the scattering angle and the coefficients of the periastrum advance in the post-Minkowskian expansion up to a factor of 2. So it all depends how you normalize these things. We're exactly the same. So this combination is exactly the same as this combination. And if you keep on going, you will find that all the even coefficients of the scattering angle are exactly the same as the periastrum advance. Once you analytically continue this guy, these coefficients from positive binding energy to negative binding energy. And in fact, the first term here was found earlier by Simon Caron-Watt and Sarah Sare, who realized that there was a connection to the amplitude and the periastrum advance. They also did not write it this way. They wrote it similar to what V and company did by removing the pole in 1/q in the transfer momentum of the amplitude. But if you Fourier transform, you realize that this wants to be a function of R because that's literally the p squared. But we show exactly how to extend this to all orders. And this was also picked up by Julio and company when they studied the supergravity case, because there's a 0 here for the triangle in the supergravity case that suggested that there was no periastrum advance. But once you see how this keeps on going, you realize that it's very likely that we will get a non-zero periastrum advance because the M3 is not 0. But this is very nice because this shows how you can connect directly the amplitude to all the observables through this radial action. But by noticing that those two things are the same, you start wondering, well, wait a second, what's happening? Is this true to all orders? And in fact, once you see what you're doing, that you're actually integrating the same thing over just different endpoints, then all you need to realize is that the endpoints are actually connected. We found, and this is actually quite nice, and I don't have time to explain, is using this first of representation, that the endpoints of the orbit, the zeros of PR, of the radial momentum, what is so-called orbital elements of the unbound and bound case are related by analytic continuation. We did this with impact parameter, so you complexify the impact parameter, but you can also do it with the angular momentum. And it turns out that the zeros of the ellipse, if you want, of the elliptic motion, are given by analytic continuation of the zeros of the hyperbolic motion. And then you look at this and you say, okay, I'm integrating the exact same thing, only changing the endpoints, but the endpoints are related by analytic continuation. So why don't I just loop around infinity and come back? So if you do that, then you realize that you pick at J minus J, but this is odd under J goes to minus J, so you get minus minus, you get plus, and then you kill the part that is infinity here, and you end up going between r minus of j of angular momentum j to r minus of minus j, which is r plus, which is exactly this guy. And then you found out exactly what we show order by order in the PM expansion is just a reflection of the fact that you're integrating the same thing. The radial action is the same thing between different endpoints with positive and negative binding energy. And that essentially gives you this remarkable connection between the scattering angle and the periastrum advance directly through the radial action without having to mention now the scattering amplitude. So this means that I can now reconstruct the radial action entirely within the classical regime without having to go through the scattering amplitude by computing the scattering angle. And this is what we did. And using this relationship here that you can integrate, because remember the derivative gives you, the derivative with respect to j gives you the periastrum, the derivative with respect to j of the unbound case gives you the angle, so you can integrate, and then essentially you can reconstruct the radial action. But if you write it in terms of the radial action, it's literally the same we did before. This plus came because we took a derivative and then we brought down this square root. But if we don't bring down the square root, then obviously that the PR will be even, and therefore there will be a minus here. So what we did with the angle and the periastrum is a reflection of what happens with the radial action itself. And because the radial action itself is an analytic continuation of each other, then we can reconstruct now the bound radial action if you know the unbound radial action, which is constructed in terms of the scattering angle. And because we kill the odd terms, only the even terms contribute. And this is just an energy factor that you can fit and in the large J limit is very easy. It's related to the time delay. So negative binding energies analytically continue the scattering angle, and we get the bound radial action. So let's pause for a second. That means that if you handle me the scattering angle by whichever mean you want, it doesn't have to be the scattering amplitude anymore. You can do this classically. You can do this by any method. I can reconstruct the radial action and compute all the observables of the conservative sector so far of the two-body problem. So this is very nice because this tells us that if we know the scattering angle, we solve the problem. So this will be for us our goal. So trying to construct the scattering data, gauge invariant scattering data, in this case in the form of the scattering angle and the bound radial action through the unbound radial action. We also show, and this is actually quite nice, and I don't have time to fully explain how it works, but we can discuss it later, is that this map that I just explained was for the non-spinning sector. So I analytically continue in the scattering, in the angular momentum, but this is the orbital angular momentum. So what happens if you put spin? Well, if you put spin, you have a total angular momentum, and we can also show, because the manipulations that we used to do the analytic continuation essentially follows very similarly from the non-spinning case, that if you use the canonical total angular momentum, the same formula applies. And therefore, the relationship that I told you between the bound and unbound radial action also applies when you put spin. For example, if you apply, if you introduce spin through the usual curve parameter, but we're doing a line spin. So in this case, you have to be a little bit careful to define these objects in general. So if you restrict yourself to the plane, so you have planar motion, so you have a line spins, then you don't have so many of the gauge issues to define the covariant versus canonical spin are gone. So it's much easier to set up the problem. This is something that is also relevant for gravitational waveforms so far. I mean, eventually we would love to have a generalization of this, but for so far we have the planar case, but already we can include spin, even if it's the aligned spin case, by doing the same analytic continuation, by reconstructing again the radial action. The difference now is that it's not only going to be even terms as before with quadratic spin terms, but the spin orbit terms are going to be related to the odd coefficients in the expansion and in angular momentum. But the same is going to apply as we did before, and very recently we solved the spinning case as well. So very good. So let me also make a few comments about how this is going to work. So we did an analytic continuation. So what's happening here is that both radial actions admit this post-Minkowskian expansion. They are both expansions in g Newton. That's what is hidden in this little j, which is the angular momentum divided by gm mu. And therefore, this expansion in g Newton is linked to an expansion in 1 over the angular momentum. Let's stick to the non-spinning case here. So it's the orbital angular momentum. So we can analytically continue to very large angular momentum and then go around, if you want, to the unbound case, because what we do in essentially is pick up what these coefficients are. And these coefficients, how do they map between the bound and unbound case? It's the analytic continuation in the binding energy from positive binding energy to negative binding energy. So this is a formal way to connect the two radial actions, the bound and unbound radial actions, which both admit this expansion, by doing this trick of large eccentricity, if you want, or large angular momentum, and picking up these coefficients by analytic continuation. Now, there's obviously a caveat here, which is we're doing a post-Minkowskian expansion, and we know that in post-Newtonian we need different orders. So how are we going to do that? How are we going to incorporate the post-Newtonian information that we need to use the PM to the same PN order? Because as we know, these are all mixed. But what happens here is that, as many of you know, is that in the binding case, so the energy is as like a PM parameter, it's a V squared, so it's like a PM parameter now. So the typical, what we use as P infinity in the scattering problem that goes into the binding energy becomes a PN parameter. The angular momentum also scales with powers of the 1/J scales also with powers of V. And therefore we can power count in post-Newtonian what is it that we're missing. The other thing that you realize is that we get the even coefficients. So what happens if I have the 3 PM? I don't have the chi4, I have the chi3. How do I input that information? But that's where this impetus formula comes. This is a very nice way to reorganize the calculation that I showed at the beginning. So if you compute, for example, the chi3, the third post-Minkowskian order that we have computed, and it was also computed earlier by SB and collaborators, you can extract a large fraction of the chi4 of the 4 post-Minkowskian order. What you don't have is the fourth order in the expansion of the P square, but the P1, the P2, and the P3, you can extract from here, which is the expansion of the P square. You can plug it back in here, and the stuff that you are missing, since it's PN suppressed, you don't care to the order that is comparable with your PM expansion. Therefore, if you go to second post-Newtonian order, which is the third post-Minkowskian order, these coefficients here are enough to basically map all the information that you want to second post-Newtonian order. But at the same time, you're including a lot of the true answer to all orders in velocity at each order in 1/J, which you can reproduce by these P coefficients, which is essentially how this map is working. So very good. So this was a sort of like a lightning sort of review of what we have done and I have presented in the past for the conservative sector. So now the next frontier will be radiation effect. It's the next frontier because we want to radiate to compute the gravitational waveforms, but also because radiation reaction effects will have conservative contributions that will need to include a 4 PM. This P4 is not just the potential part, there is also a radiation sector contribution that we need to compute. So the first question that you might ask is, okay, we related the radial actions, we related the conservative contributions, say the periastrum advance to the scattering angle and so on. How can we now compute observables for the radiation sector? For example, what is the total energy radiated in one orbit of an unbound hyperbolic encounter, which you can just integrate the flux between minus and plus infinity, and the exact same thing that you can do in one orbit, the same flux, the same function, which again is a local function of, I'll get to that later when we start including teleffects, so let's ignore for now all the non-local contributions. Let's just talk about the source contributions to the fluxes, which is a local expansion in 1/R. It's a function of R, J, and energy, as I wrote in here. How can we relate now the integral of that flux over one period to the integral of that flux in hyperbolic motion? And now comes the key part. The key part is because we are using an adiabatic expansion, we're just computing the source part. So we're really finding the solution of the orbit on the unperturbed solution, meaning without including the radiation. So this is the conservative solution. And therefore we can rewrite these intervals the same way that I wrote the radial action, the exact same way. It's twice because we go from R, the bound R minus to infinity twice and back in time, or between R plus and R minus, the two halves, right? But it's the same integral as before. This is a function of Rj and energy. This R dot is a derivative, if you want, of the Hamiltonian with respect to PR. So it's a function of J and energy and angular momentum as well. So how are those two related? Well, it's actually quite easy to see what's happening here once you realize that the flux is an even function of the angular momentum. There are many ways to see this. It's actually an expansion of p squared and pr squared in the isotropic gauge. You cannot do isotropic both of them, but you can write as a function of the full p squared and pr squared, which is a function of g squared. You can also think that you basically going this way or going this way is the same. And the r dot is also an even function of j squared. So once you input this in here, and we know that the orbital angular elements are related, it's very easy to loop around again. The difference is that now there's a plus here. Before, between the periastrum and the angle, there was the j over pr, and that j upstairs made it odd, and therefore it was a plus. But here, because it's even, you get a minus. So it's actually quite straightforward to say those two things are related when you do this approximation in which you find the solution on the conservative solution in this adiabatic approximation. It's very easy to see that the analytic continuation now of the hyperbolic radiation is related to the elliptic. And this was also noticed by Bini and Damour, who actually looked at the solution to some post-Newtonian order, and they realized as well that you can do this analytic continuation and get from hyperbolic to elliptic, but the reason to all post-Minkowskian order is the same reason that we can connect everything, is this analytic continuation of the orbital elements. So now this is very nice, and notice that I'm gonna go a little bit backwards, and the way that also Thibaut and Donato realized that this was also compatible with our previous map in the conservative sector, because there's something that is known in the literature, that there's a way to relate this so-called tail effect, and also we mentioned this, to the fluxes. And because the tail effect in the conservative sector also contributes to the conservative radial action, if our map continues to hold in the conservative sector, then this has to be true because it's a consequence of our previous map. And therefore there's a circle here, everything goes in the same direction. However, I'm now going in the other way. I'm proving this first, and I'm using this to show that the conservative map will also hold. Oh, by the way, let me mention something very quickly. The same applies to the orbital angular momentum. I think this is actually very nice. And it works, as you will see, it works for a lot of things. What happens here, this guy is odd. This actually starts with P5, it starts with J. So this guy gets a minus sign here, so it goes to plus. And you can also go and check onto all post-Newtonian orders that the elliptic total flux of angular momentum in one orbit is related to the hyperbolic case as well, but you have to kill, in this case, the same way that we did before, the odd terms. 1 over j squared, same guy. So it's actually quite nice. This is so powerful that as long as we are in this approximation in which we do the adiabatic approximation, and we assume the conservative solution to compute the fluxes, almost everything goes, which is quite neat. But let me go back to what I said before, because the question that you might ask now is, what about the conservative part of the radiative effects? And probably I don't have much time to explain this, but it's actually very nice. And it was noticed a long time ago by Walter Goldberger and Andy Ross, that when they computed the tail, like the amplitude in the emission of the tail term, your power counted in GM omega. Every tail interaction gives you GM omega, and this is understood in PN as well, right? But this is very nice because this GM omega, if you realize that this is the spectrum, the rate of emission of gravitons, if you multiply the rate by omega, you get the spectrum. Then you realize that the imaginary part of the self-energy term, which if you use the optical theorem and you cut, give you the total radiated energy, it has to come with the spectrum. So the imaginary part is the spectrum from the source term, just the source term. Obviously, this doesn't have the tails in it. But this is very nice because that means, and if you go ahead, and now you do the tail contribution, which we computed also some time ago, and you do it in the in boundary condition, not with Feynman that will give you the wrong answer, as also I think it's going to be discussed by Ricardo later. You have to be very careful with the boundary conditions. But if you do it with retarded boundary conditions, which we did a long time ago, then you realize that the only difference, at least for this guy, is just how you treat the poles and how you treat this odd versus the I pi base of the I pi sine of omega, the odd versus even terms in omega. But this coefficient here is exactly the same. And in fact, it was also recently used by Luke and collaborators. I think Luke didn't have time to talk about it because this is universal and you can resum all these logs in this fashion. But it also tells you that this guy is going to crawl in here. The spectrum is crawling into the real part now of the conservative sector in the true calculation with the retarded boundary conditions. And therefore, if this flux can be related in this way because now the effective action, which you can, if you look at the perturbations at this order, you can treat as an integral of the tail Hamiltonian. This was actually nicely shown by Donato and Thibault. And this is literally the H Hamiltonian comes from the effective action. And this is proportional to the flux. Now I'm going backwards, right? Because this is true, I can show that this is true. And therefore, the binary to bind dictionary that relates the bound and unbound radial action works also for the local part of the conservative sector, and I can apply it the exact same way as we did before. We can also demonstrate this backwards. We can run all this the other way. It's a little bit more subtle, but you can also show that the local map works, and therefore this has to be true as well. And this is very nice, and we can do it also with the orbital angular momentum. I can do it also for the non-local part. However, the non-local part is really tricky. And this is something that's also understood from the post-Newtonian point of view. Now that I demonstrate to you that we are evaluating everything on the conservative solution, even the non-local term, we will evaluate on the conservative. So it's non-local because it's an integral of this split flux, but the solution that I'm going to plug is the solution of the conserved orbit, or say if you compute it for circular or quasi-circular orbits, then this still works. I can use the same analytic continuation. So if the tail Hamiltonian of the non-local part, which is this log that I showed you before, also obeys the symmetry, then these two are related. And lo and behold, we checked, and it's symmetric. It's even under j goes to minus j. So now even the total non-local part of the conservative tail also map this way. However, here comes the catch. The catch is that we're doing a large j expansion, a large angular momentum expansion. So this is, you have to be very careful here, because before, for the local terms, the large j expansion, it was the same because you admit a 1/j expansion of the answer, even if you're doing small eccentricity. The solution can be continued to large j, and the coefficients on top are the same. So you don't care. However, this guy is no local. So this doesn't go so nicely between the large j limit and the small eccentricity expansion. So naively, we can construct the average Hamiltonian for the non-local term in the large j expansion, and we have checked explicitly that it maps through this non-analytic continuation. However, we have to be a little bit more clever to relate this to the Hamiltonian in the small eccentricity expansion. It does not work literally just using this for a small eccentricity, but we know the form of this guy. We know it exactly. All the terms that we don't know are the local terms that do go through this map, as just show you. So all the non-universal pieces that we need to calculate, they will go through the map unscathed. We just compute them, they are there for the bound, they are there for the unbound, they are there for the bound, we're done. Everything else that we're missing is universal. So we can compute it and then put it back in any case that you want. The log is universal, as Luke and company found, used as well. The pole is universal because it has to cancel the pole from potentials. And this guy has been even computed to 3 p.m. So we even know right now what the answer is. We just need to do this integral, and we are doing it. Because we even know right now what the answer for the tail should be, because we know all these terms are universal. So now when we're gonna do the boundary to bound map, we can carefully map the spectrum, not the total answer. And here we kind of go a little bit off shell if you want, because we have to have control of this guy, which in the amplitude business is a little bit trickier, because they computed the total radiated part, whereas in the IPhT side, due to the matching of the T mu, computing the integrand of this is semi-trivial. We have this already. It's actually 2 diagrams. So we have a lot of control of the tail terms. The missing ones are the harder ones, the ones that we're computing. So how are we going to calculate this? This is the second part of my talk. So hopefully I convince you that we can do a lot on the radiation sector as well. And now the task that remains for us is to compute the conservative problem, the scattering problem, not only including the potentials, but also including the radiation modes. And how are we going to do that? And that comes the second part. And I have no idea how much time I have. How much time I have? Some 15 minutes. And
5 minutes.
How much?
5.
Oh, you should have told me earlier. Okay, so good, 5 minutes. So this is going to be quick. So many of you have seen this already. So in the effective theory approach for post-Newtonian, we have this effective action. We interact. It's actually the Fokker action, if you want. Okay, let's make it simple. The Warland action we have used since a long time. There is the point particle, which you can do Polyakov here, which is nice. The spin I did many years ago. Finite size effects can be included to Warland spin square terms and also tidal effects. We already showed that you don't have to be afraid of Feynman. We can use a lot of tricks to reduce the number of the number of terms in each interaction. And here what we have is initial data. The initial data is the initial velocities, impact parameter, and spin. We go ahead and compute this effective action. We plug the solution in the action. We take derivatives. We get the impulse, both impulse, spin, and momentum. We get the scattering angle. And this is what we do. We just iterate, and we have found solutions just by finding iterated Green function, the same way that you do loop integrals in field theory. Now, this is not new. This was done a long time ago in NRGR. For the binary case, this was done by Ira and Walter. Now, this whole issue about I epsilon prescriptions is non-trivial, as it has been emphasized by Thibaut many times, and we have solved since many years ago as well. The potentials, the I epsilon, nobody cares because it's out of shell. So as long as you do potentials, nobody cares. The total flux, you can use the optical theorem, so you can use Feynman and cut, which is what amplitude people do, and therefore the I epsilon is Feynman, and everybody's happy. But if you're gonna do now radiation reaction effects and initial value problems, you have to do the Schwinger-Keldysh formalism, and this is what we are doing right now. We're doing the extension of our two scattering problem in effective theory in the Schwinger-Keldysh formalism, which just tells you that you have to double things. Just your propagators instead of Feynman become retarded and advanced. It's just a little bit more complication, but conceptually it's very easy. It's exactly the same as before. You just go to this physical limit in which you take a derivative to x minus, and you go to the x minus goes to 0, x plus goes to physical. You go to the center of mass, you can compute the angle and the total radiated energy. Of course, this is very difficult to actually separate if you go to the center of mass when you have recoil. But as long as we're dealing with the conservative part, it's all fine, or to 3 p.m., then we don't care about recoil anyway. This has been done before. We did it to complete the 4 post-Newtonian order. There was the first calculation of the tails this wage, which we did here. We found the 42/30 that gave a lot of trouble to the traditional approaches. We found the cancellation that we show with IRA between what happens here, because we separate between potentials and radiation. You're spoiling the IR by doing this expansion. You're spoiling the UV by doing the multiple expansion, but obviously those two regions, they are overlapping if you have these IR divergences, but the divergences have to cancel. This is connected to this 0 mode factorization, which I don't have time to explain, but we did this to do 4PN. So we have control over this already in post-Newtonian. In fact, I'm sure Ricardo is going to talk about how you can do hereditary effects to next to in order to do 5PN. And even the potentials can be taken recently by Johannes, Peter, and Andreas, which did the 5PN potential. So this is a machinery that we understand very well. So can we do it now in Post-Minkowskian? Well, now the difference is that we have the full south region. So not just potential, not just radiation, but the whole thing. And now I don't like this soft region thing because there's a quantum summation as well, but let's just call soft potential plus radiation, and everybody's happy. So as we learn also from SPI, we can do differential equations here. This was a beautiful paper by Julio, Mao, and Michèle, who show how to do this. In this case of the supergravity case that we discussed, we took this to solve the 3PM almost straightforwardly. In the GR case, the main idea now is that you solve the differential equations, which is single scale, that basically resounds all the velocities. All you care about whether there are potentials of radiation is the boundary conditions. And as long as you have the correct integrand that you do in ININ, then you have the complete answer. And we are now in complete control of the next to next to in order integrand and the full conservative next to in order integrand as well. So we have the full self-conservative integrand, which includes terms that I believe Spear and company did not include. That includes all the self contributions, if you want, self-energy contribution, what they call mushrooms, that contribute also to radiation reaction that we control here through the retarded boundary conditions. We almost have, I would say we solved the differential equations, but we can discuss this during the meeting. The difficult part for us has been these boundary conditions. And recently, since we saw the paper by SB and collaborator, we decided, okay, let's check the potential. I want to do the full thing without poles because this is finite. This whole splitting, these ambiguities are gone. And if we solve the differential equations, we don't even have to PN expand. We solve the problem. Once you input the boundary conditions, you are done. And actually, the potentials turn out to be quite simple. The boundary conditions, they took a little while for us to do, but actually they were not that hard at the end in retrospect, and there are only a few. So actually, this business of differential equation is really powerful, and we're going for the full answer. So as you guys know, we did the 3PM. The potentials are enough. And we computed the 3PM, the P3, which is the guy that we need to input all the information from the Chi3 that goes into the radial action, from which you get the periastrum advance, from which you can get all the observables, including a spin that I don't have time to explain. So since I probably have to wrap up, and I can answer questions if you want about the recent results on spin and so on later, let me just say that this formalism that we introduced is extremely useful because it lands directly in the classical integral. It gives us what is the self-expanded, so the large impact parameter expansion, the large mass expansion is all taken care of from the beginning. We get just these massless integrals, which in principle we can solve exactly the same way that you do it in particle physics through these differential equations. The nice thing is that we don't get these IR divergences from these so-called superclassical terms. There are no infrared UV splitting from regions. If we can control the full classical soft expansion, and by doing the boundary to bound dictionary, we don't even have to go to the Hamiltonian. We can just directly manipulate the answer, the radial action, and map that information from bound to unbound. And we are now working on the 4 Post-Minkowskian order, and hopefully this will be resolved during the time of the meeting, or hopefully in the near future. So let me just show you quickly how this works. So you compute the periastrum with the P3, and then you see how all the post-Newtonian orders, for example, the while loop is exact. This is just beautiful. At all PN orders, we predicted this guy, and then you go on 5 PN, 6 PN, and you fix it. Obviously, we have to truncate it up to 2 PM because that's what you get. At 3 PM, as I was saying, you can get all the observables without Hamiltonian. The spinning case we study first by looking at data from post-Newtonian, but eventually we solve it exactly. This is one of the most beautiful formulas I've seen. This is the radial action for the 2 PM problem, which is just from the angle. So this is the spinless part, but this is the spinning part, just from the angle. You get the full answer for the bound case. For example, the periastrum advance to all orders in velocity and spin square directly from the scattering angle to the bound to bound dictionary. And we also confirm this scattering angle calculation using different methods for the Kerr case. We did the full answer for the impulses for genetic orientations. We also checked and confirmed a concurrent calculation by Andres and Dimitros on the spin square term. So everything seems to be convergent, and we seem to be having a lot of nice data that we can match to the bound case. We also did tidal effects, from which we got some new information that also Luke discussed, and then there's beautiful connections between scattering data and binary systems, and I think this is just the beginning. And hopefully this 4 PM will come out soon from our side with a full soft answer that will resolve these ambiguities, this pole, this issue that we had between potentials, separation between potentials and radiation that we don't see in Post-Minkowskian. Hopefully we'll get the answer soon, and thank you very much, and sorry for going maybe a few minutes over time. Sorry, Anne. Thank you.
Thank you, Rafael. Let's do a virtual clap. Are there any questions? Can you put your virtual hand up if there are, please? David. Kosower.
Oh, where are you, David?
Oh, no, his hand's down.
Oh, come on, ask me a question.
We've got a couple of minutes for questions. Oh, David was a clap, not a raised hand.
Okay, that's good too. Oh, by the way, I should say, so we were very much motivated by Kosower, maybe O'Connell, that did the scattering case on show without going to the Hamiltonian. Our idea was how to use that for the bound case, how to map the information to the bound case without having to go through the Hamiltonian, which is this whole idea of the unbound-bound relationship, the dictionary. But this is beautiful as well, and this is actually very interesting to find out how they deal with the self-radiation, because how they deal with the boundary conditions in mean versus what they did is actually quite interesting.
Okay, since we are running slightly late, and
Paolo is asking a question.
Yeah, my question is why you write P3 putting only the conservative part? Why don't you add in P3 also the radiation reaction? The amplitude in GR at 3pn is completely known.
Yeah, because I computed P3 from the conservative part only.
Why?
Oh, because we haven't done yet the full thing. We are almost done with the full thing. So we computed this integral at 3 p.m. only from the potentials. When we did the conservative sector here, we only kept the potential modes because these guys are there, and you're completely right, and we are almost done with that. But those are dissipative, purely dissipative. And therefore, we just care about conservative, we don't care. At 4 p.m.,
no,
yes.
But the whole thing is already known, both in our paper and in the paper by Thibault.
Absolutely, they're known,
Yeah.
but they don't map. I don't need them for the dictionary to the bound case. I want to keep the conservative sector and map the fluxes independently. That seems to be much more powerful. Keep the conservative. We do this in the adiabatic expansion in post-Newtonian, and here it seems to be the best way to go as well. Rather than finding the whole radiation reaction force instantaneously, let's do an adiabatic expansion and solve the problem. Conservative, dissipative, separate. And for now, at least for post-Newtonian sources, this seems to be the way to go and helps tremendously to ignore this, compute the flux, rather than finding the radiation reaction force instantaneously and so on. So it's just phenomenologically more convenient.
But Rafael,
yes.
But since since we do have the iconal, the exact iconal at 3 p.m. sorry, including radiation, why do you have the impulse or whatever you call it?
We will
the PR, the radial action too, at that order? Why don't you continue directly that?
Because I want to rederive it my way. Are we almost done with the calculation at 3 p.m. of the full answer, including radiation reaction and conservative potentials? And at 4 p.m., I'm computing everything.
And then you can check if the continuation works. Is that the idea?
Yes. But what I was trying to tell to Paolo is that the continuation of the conservative sector and the dissipation, they work separately. And because when I do adiabatic approximation to do waveforms, I do this separately, or most of the time I do this separately, say. This seems to be more convenient. Compute flux here, compute conservative here, and then map them through this dictionary and compute the waveforms here. That I found much easier because the fluxes, as I explained earlier, are way easier to calculate than your icona. I can compute in really one line the spectrum at 3 p.m. It's just 2-3 level diagrams. Now, it's much harder to get that from the full two-loop calculation, as we know from Julio and company and your calculation. The integral is hard, but setting up the integrand is very easy from the point of view of these fluxes. So we found that more convenient, or I find it more convenient. I think Thibault also make the same point from the post-Newtonian point of view. It's much easier for us to split the problem this way. That's the only reason.
But it seems to me that to get the correct radial action from the amplitude, the problem is the conservative part. Once you solve this, the radiative part comes automatically. You don't have to do anything because the terms that appear in the deflection angle are exactly the terms that appear in the amplitude for the radiative part. But instead, for the conservative part, you have to do some subtraction. And this subtraction essentially is more or less a subtraction that we do with the iconal.
Okay.
So I don't see the...
That's because you are thinking about amplitudes. I'm not doing amplitudes anymore. I don't have to subtract anything, right? And in the effective theory, we separate what is radiation and what is potential, naturally. And for us, that separation, even though we are doing Post-Minkowskian and resumming everything, we know poles, blah, blah, that separation seems to be still very useful for us. I will agree with you if I was doing amplitude, that you get everything in one go. For us, and also in the effective theory, it turned out to be much easier to do this matching of the T mu, square it and get fluxes and solve the potentials independently. That seemed to be much more efficient to compute the integrands that do the full amplitude at once. I can show you very easily, and we can discuss this during the workshop, that doing the two-loop calculation that Julio did takes much more work than finding directly what the T mu is at GQ, which is literally one line. So we found this to be much easier. That's all. Conceptually, I will agree with you, but the calculation is just harder.
I think we should close there and thank Rafael for a brilliant talk and stimulating questions, and perhaps move on to the next speaker. Thank you, Rafael.
Yeah, thank you, Anne.
Is Gregory around?
Yes, I'm here.
Great.
Do you see my screen?
Yes.
Wonderful.
Okay.
Well, hello, everyone.
Let me introduce you, Gregory. It's a great pleasure to be able to introduce Gregory Gabadadze, who's just removed his title. He'll be talking about gravitational dressing of conformal Galileons. Over to you, Gregory.
Thank you, Anne. Well, it's good to see you all or hear you all. And thanks for inviting. Let me briefly describe what my talk is going to be about. We all know by this time, I suppose, that there are certain theories of scalar fields called Galileons, or their extensions such as conformal Galileons. These are self-interacting theories which have derivative interactions as opposed to polynomial interactions of potentials that we prefer to consider for all kinds of applications. Usually those derivative interactions are problematic because they give rise to more than 2-time derivatives in classical equations of motion, and the Galileons distinguish themselves by the fact that they preserve 2-time derivatives in the classical equations of motion, and hence all the interest to understand these theories and perhaps use them. There were many papers with proposals for cosmological, astrophysical applications of Galileons and so on and so forth. The question that I will be addressing today is whether these theories can be part of bigger, generally covariant theories, and Galileons or conformal Galileons just emerging as actually some gauge part or gauge mode of that bigger theory. Example of which already exists for Galileons, which I will allude to, but I'll be talking about conformal Galileons and trying to address them gravitationally. That's what it means. What I don't mean is to take a scalar field theory such as Galileon or conformal Galileon and try to covariantize it. That's by itself interesting route. People have pursued that, but that's not what I'm going to be doing. I will be embedding these theories into, well, tensor fields or related fields to tensor fields, so that they are, in the full theory, they are gauge modes, and it's only in a special limit they emerge as standalone by themselves interesting scalar field theories. That's a philosophy. So let me begin with the Galileons. That's a theory of a scalar field, usually called pi. I'll be talking about 3+1 dimensional space-time, although this is generalizable to other dimensions. The list of Galileons, or Galileon actions, is given here. It's a finite number of terms, and the number depends on the dimensionality of space-time. And it is easy to generate the next term from the previous one. You just multiply pi by certain contraction of the epsilon tensors. These are Levi-Civita tensors contracted with two derivatives of little pi. Capital Pi is two derivatives of little pi. If you think of it as a matrix, this is all possible contractions. I'm sorry, it's not all possible contractions. It's a contraction of that matrix with two epsilon tensors in a natural way, so that it's non-zero, and the rest of the indices are contracted with themselves. And you just move up in powers of the capital Pi, starting with power 0, 1, 2, 3, 4, and 4 is the maximal that you can do, because the epsilon tensor in 4D has only 4 indices. In 5D, you would have had one more term, and in 3D, you would have had one less term, and so on and so forth. This is pretty clear. So these terms, at least the first two, are kind of well known in a different form. The A1 would be just kinetic term for this pi, and the A2 would be what's called the cubic Galileon. Actually, that was the first one discovered in the paper by Porati et al. And then the generalization was given. So these theories, as you can see, have irrelevant operators if you think in terms of a renormalization group and quantum field theory. Everything besides A2 has dimensionality greater than 4. Therefore, if you were to write down an effective action, you would have to put in some dimension full parameter or a scale by which these higher dimensional operators are suppressed. And then there are a host of issues as to why you can terminate at this point and not include all the other terms, and so on and so forth. So all these questions are interesting ones and relevant ones. They have been answered in the literature. I will just run quickly through them because I'm pursuing somewhat different goal. So the point is that these terms are somewhat special. They differ from the typical higher derivative terms, not only classically, as I mentioned, giving second order differential equation, but also as an effective quantum field theory, because they have less derivatives than, for instance, if I were to write down here a cubic term, one possibility is of course box pi cubed, which would have had 2 more derivatives. And if you are thinking of low momenta as compared to that scale, then this term would be dominant on the other one, and so on and so forth. And people worked out some prescription how to think about this as an effective field theory, still having this term dominating over the other ones. But what I would like to emphasize is that these terms are part of or emerge as components of tensor field in massive gravity. So if you were to write down a massive gravity action without introducing any scalar fields, and if you were to focus on a helicity 0 component of that massive spin 2 field, then in a certain limit, which is similar to high energy scattering limit, you would have discovered, or you would discover, these Galilean terms with certain coefficients, and so on and so forth. So in other words, the moral of the story that I would like to extend is that Galileons are natural parts of massive spin 2 nonlinear theory. And I would like to ask the same question about extensions of the Galileons, such as conformal Galileons. So before I go there, let me mention something about symmetries. So this Galilean theory says, that's why the name, they possess a symmetry, which can be thought as a 15 parameter group. 10 out of those 15 is usual Poincare, as you can see, but then there are 5 more generators. One corresponds to just shift of pi. That's like when you have a Nambu-Goldstone boson, you have shift symmetry that's similar to that. But then there is another 4 parameter which corresponds to shift of this pi with x mu times some c mu, x mu being a coordinate. Or if you think in terms of the derivative of pi, then that latter symmetry is a shift of derivative of pi, and that looks like a Galilean transformation in a usual sense, because the velocity is being shifted by a constant. So that's where the name is coming from. although this is a Galilean transformation in the field space, not in the coordinate space, and that's the name. Okay, now let me go to, I wonder, do you see 2 pages when I show this, or you only see 1 page?
2 pages.
Okay, so 2 pages, great. So then on the second page, on the right page, you see a generalization of this theory, which is called conformal Galileon. And this theory has very similar properties of the previous one in terms of equations of motion being a second order and Cauchy problem defined by using just initial condition for the field and derivative. But the symmetries are different. Namely, conformal Galileon realizes non-linearly the dilatation and spatial conformal transformation of that field, and linearly the Poincare symmetry of 4-dimensional space-time in this case. And the actions, again, terms in the actions are, the first one is e to the 4 pi, and I'm sorry, that's called the zeros. And the first one is kinetic term times e to the 2 pi. And then there is this one, which has a cubic interaction. And the first piece in that cubic interaction is what was called before the cubic Galileon. And then there is another one with special coefficient, which is d pi to the 4th actually, and so on and so forth. And again, you have finite number of them because of the same nature. Now, what's interesting was that this theory was constructed as an effective field theory using a coset.
The other one to be there.
Using a coset, the coset formalism. So if you start with flat space, we're talking about flat space at this point. There's no gravity or anything yet introduced. And if you start with a conformal group in 4 dimensions, which is SO 3,2, and mod out by the Poincare group in 4 dimensions, which is ISO 3,1, you have 5 generators non-linearly realized and 10 linearly realized because of the coset. So you can follow the standard construction of, Callan et al. Of 1969, I think, or 68, and generalized to non-compact symmetry, space-time symmetries by Ogievetsky and Volkov and others, and follow that procedure as was done in this very nice paper by the authors listed here, and construct these terms. So what you will find that indeed you can build A0, A1, A3, and A4 as just terms of the coset, as if you were doing, for instance, the chiral perturbation theory for QCD, for pions. This is very similar construction to it. It's just the group theory is different, but philosophically it's very similar. So you get all these terms except A2. But for A2, you will find out that there is a Wess-Zumino term, which is not the usual coset term, because you start with one higher dimension, 5, and then you identify a form, which is a total derivative of somebody, and then a pullback of that form onto a boundary will give you A2. So that's just the Wess-Zumino term in that construction. So this is what was known. And my former student, Georgi Tukhashvili, and myself, we set out to try to embed this theory into some gravitational theory, which obviously we don't know a priori, or we didn't know a priori what would be, so that these modes emerge as some gauge modes in that gravitational theory, as the simple Galileons emerge as a gauge modes of massive gravity. All right, so the next page is mostly a summary of notations, because this is a formalism that I alluded to, which is broadly known. I'm not going to go into too much of technicalities, but I wanted to write few expressions here, essentially to set the notations. So we're going to look at, fully generally covariant theory, which would manifest spontaneously broken conformal symmetry down to gauged Poincare, obviously, to have full general relativity. And so the concept that we're talking about is very similar to the one that I mentioned, and here it can be made general. In fact, we considered 3-dimensional case and 4-dimensional case, and I will focus on 4-dimensional case because that's more relevant for real world. But 3-dimensional case is also very interesting. I will summarize the result for that case in my last slide. So in 4 dimensions, it's SO4, 2. In fact, on my previous slide, I had a typo. Had to be SO4, 2. I said SO3, 2. That was 3-dimensional part. So this is the group element here, and the Morer-Cartan form is built this way. And the next step is you expand this in the basis, because it's a one form in the algebra. So expand in the basis where P denotes the generator of Poincare transformations. K, as usual, is generator for special conformal. This D here is dilatations, and J stands for Lorentz generators, obviously. And the coefficients, the capital A, capital Omega, capital Omega sub K, Omega sub D, which are coefficients of this expansion, they are calculable, obviously, knowing all these expressions and knowing the commutation relations for 4-dimensional conformal algebra, so that you can calculate. And this is what you will get, that the capital A will be e to the pi times the Vierbein. This is a Vierbein of GR. And capital D will be, this one here stands as a covariant derivative. I'm using the same notation for dilatations and covariant derivatives, but from context, it's clear which one is what. Covariant derivative pi plus capital E contracted with zeta, and so on and so forth. You can determine all these quantities. That's the point I'm making. And then I'm going to be using the notations for the curvatures, which are kind of 2 different notations. These are just notations for the Riemann curvature. So this is a Riemann tensor. Well, it's a 2-form. It's written in here as a 2-form. And the curly R means that it's made out of capital Omega, which is related to non-curly R, which is related to little omega. Little omega is conventional spin connection, and capital Omega is related to the little omega by some additional terms, which are there due to this conformal nature of the construction that we're doing. So they have something to do with this extra fields related to dilatations and special conformal transformations. It's just a notation. And then another object that I'll be using is 1 form, which is again curly R, and that's just inner product of the 2-form Riemann 2-form with the with inverse Vierbein essentially. But Vierbein again, conformal Vierbein, maybe I should put it, because it differs from conventional Vierbein by the conformal factor. So that's just the nomenclature, but the construction is straightforward. Now, so I'm going to list now, I think 6 terms, maybe 5, can't remember, probably 6, which come out in this construction with minimal number of derivatives starting with 0, and try to analyze as to what they are, and then understand how this conformal mode, what role does it play, what gauge field is it, and how it emerges then in the high energy limit, in the decoupling limit, how it emerges, how it gives rise to these conformal Galileons. So the zeroth derivative order is kind of almost trivial. The only term you can write is the wedge product of 4 generalized Vierbeins. And if you go into the unitary gauge, because now you can choose a gauge, you do have wild transformations, local wild transformations. If you do that, if you choose that, which is I'm just doing for simplicity, then you're gonna get just the cosmological constant. Of course, this full term is, in the original formalism, you get it in a full-fledged way without gauge fixing. And what you need to do here, substitute G by G times e to the 2 pi. And that has, of course, while invariance, local while invariance. Now, there is a subtlety here. I'm going back and forth between unitary gauge and non-unitary gauge, but that's tricky because of possible conformal anomaly. I will have to come back to that point and address. And as you will see, there will be a Wess-Zumino term taking care of the conformal anomaly. But until then, I'll be presenting this in a simplified form just for the sake of writing it on a page. Although in this case, it's in full-fledged form is also very simple, it's just the exponent, but other terms won't be that simple, as you will see. But for now, think of this as classical so that you can go back and forth easily between unitary and non-unitary gauge. For simplicity of the presentation, it's always very easy to restore a non-unitary gauge, and the full theory that you get out of this construction is obviously a non-unitary gauge local while invariant theory. So at the level of two derivatives, again, there is only one term that you can write. And in the unitary gauge, that's the Einstein-Hilbert term, but in a non-unitary gauge, you also know what it is. It's kind of while invariant Einstein-Hilbert, which will have exponent in front of here, and then the derivatives of the pi field and so on and so forth, which you can again restore by the same trick, keeping in mind possible anomaly. At the four derivative level, so there is a R wedge R. So the R, as I said, R is a two form, and then construct, wedge product of two will give you four form. That's one term, and then there is another term in which you wedge two one forms made out of the Riemann two form, as described in my couple of slides ago, but they are wedged with the generalized Vierbeins. And then there is another one in which you construct the generalized Vierbeins like you did for the basic term, the zero derivative term, but there is an R squared. Now, so overall there are three parameters. There is one overall parameter of this order, and then the two free parameters. And if you require that this theory for the pi to give you a conformal to have no more than two derivatives in the equations of motion, this will lead you to the Gauss-Bonnet term. So the combination of these terms with special coefficients will give you the Gauss-Bonnet term in the unitary gauge. So again, you can restore non-unitary gauge. It will be a complicated expression, and that's the reason why I'm not writing those things in non-unitary gauge, because you'll have all sorts of mixing of derivatives of pi's with curvatures and so on and so forth. But in its essence, it's a Gauss-Bonnet term. So far, nothing new. Well, obviously, these terms are well known, but it is interesting that the formalist recovers them in this way. And the new term, well, at least for me, a new term, and I'm curious, maybe somebody knows something about this term, emerged in the next level, at the level of 6 derivatives. So there are these terms. I don't want to tire you listing all of them. The construction is straightforward and algorithmic. So you make all sorts of four forms out of the two form and the one form and a zero form actually. And then for simplicity going to the unitary gauge, and then require no more than 2 time derivatives for the conformal mode in the equation of motion. And that gives you this term, which is some special combination of third orders of the curvatures. There is one more free coefficient here, which this procedure doesn't fix, and that coefficient gives you an arbitrary term here, which is proportional to the wild tensor with arbitrary coefficient. But I didn't include that in this writing for simplicity again, because that wild tensor vanishes when I substitute in it the conformal mode. But this is a one that gives you the A3 conformal Galileon if I were to either focus on the conformal mode of this theory Or if I started with a full-fledged while invariant theory and said, let me freeze my gravity just to a Minkowski space, so then only the while mode will be operative, obviously, and that while mode would give you exactly the conformal Galileon number 3, as it was called before. So that's the cubic. Then in the quartic order, again, the construction is straightforward. And there is 3 constraints that are being imposed on 4 parameters to make sure that the equations of motion are second order. And this is what you get, the 4th order curvatures with very special combinations. And the same comments apply to these 2. Focusing on the conformal mode, it's going to give me the conformal Galileon. So in this way, conformal Galileon is just the gauge mode here. It's just the while mode. And then it depends on to what would you like to do. To gauge away, or if you want to do cosmology, actually, as I will come to in a couple of slides, then you focus on that conformal mode, because FRW cosmology is a dynamics of conformal mode. The background evolution is covered by the conformal mode, actually. But it is pretty clear as to what this is and what it gives you. Now, a couple of words about the anomaly. So far, what I've written is action for a coset. These are all coset terms which come out through the standard construction with arbitrary coefficients. So C0 times A0, C1 A1, C2 A2, A3, and so forth. And as I said, in the construction, actually, you get action which depends on this object, which is metric times e to the 2 pi. And then I was choosing for simplicity pi equals 0. But that's not always, well, in quantum theory, there is while anomaly. So one can't quite do that. And the question is how this formalism recovers, or can it recover, can it capture the while anomaly? Turns out it can, in a very similar way to actually the QCD construction, when you want to capture pion decay into 2 gamma in the Carrel Lagrangian, or in this flat space conformal Galilean construction that I alluded to, paper by Kuhn, Hinter, Bickler, Joyce, and Troden, in which it emerged as a Best-Domino term. Here, there is also a Best-Domino term, which is a total derivative of another form. And if you do that computation, which I'm skipping here for simplicity, actually you will recover remarkably this term, which has been discussed in the literature recently in a different context of proving the A theorem for the for the RG flow. Here you recover it, obviously in a classical approach, because that's the Best-Domino term capturing the quantum nature of anomaly. And its form is that you got this pi field times the Gauss-Bonnet combination, and then there is characteristic d mu pi times the Einstein tensor, and then this piece is actually the cubic part of the cubic conformal Galileon, the combination of the cubic Galileon and the d pi to the 4th with the proper coefficients. So the full action, the full total action, which is sum of the coset I call, and the Best-Domino, has this form. One has to take this A coset, in which now field is g times e to the 2 pi, and then one has to add the Best-Domino term, which is just written here. So that completes a theory and answers the question as to what is the theory that gives you the conformal Galileons. In fact, I should point out that this gives you the cubic conformal Galileon, the Best-Domino term, and that is consistent with the flat space construction as well, in which it was also a Best-Domino term. So now, what can you do with this theory? Why this is useful, besides the fact that it's a very special combination of obviously linear and quadratic curvatures, which is Gauss-Bonnet well known, but the cubic and quartic, they also seem special in a sense that conformal mode gives you, conformal Galileons, hence having the second order equations of motion. So is there any use in cosmology? Well, before you think of any use, of course, you got to worry about the higher derivatives that the r cubes and the r to the fourth introduce and what those extra degrees of freedom might be. So the fact that we've taken care of the conformal mode not having the Ostrogradsky ghost, right? So this statement about conformal mode having only two derivative equations of motion, another language is to say that there is no Ostrogradsky mode in that sector. That doesn't guarantee that there is no Ostrogradsky mode in the tensor sector, which of course is present now in the full theory, and one needs to understand that. But simple calculation, which actually is, or rather estimate, which is known for all these kinds of theories, it's not specific to this particular theory, is to limit the scope of this as an effective field theory in which the ghost or potential tensor ghost is about the cutoff of this effective field theory. And this is the comments that I have here. For instance, if you consider an arbitrary background, well, without any background, of course, there is no issue because if you are expanding around Minkowski space, you got Einstein-Hilbert term, that's all fine, and then you got the Gauss-Bonnet term at the quadratic order, that's all fine too because it's a total derivative. But at the cubic order, it's not a modification of the propagator on flat space, it's just a nonlinear interaction between the or scattering between the gravitons, and same for the quartic order. So there is no room for conversation about Ostrogradsky modes in that sense. But of course, that's kind of hiding, really hiding and not flashing out the problem. And the reason why is because the moment you consider any non-Minkowskian background, those cubic incurvature and quartic incurvature terms will give you modifications of the propagator, a quadratic piece on that background, and those modifications will in general have additional derivatives up to well, for sure 4, and that's enough for having a ghost. But then there is an approach in terms of effective field theory to limit the scope so that the ghost is mass of the ghost is about the cutoff, and this is what's done here. So if I have some background for which the metric I denote by G super B, B stands for background, and H is a fluctuation about that background, and I assume that the backgrounds have curvatures which are much smaller than Planck squared, right? So that's a reasonable assumption because we don't want to go into the realm of quantum gravity where curvatures would be of order of m Planck square. So we're staying in the classical or quasi-classical approximation by this condition. And if so, then of course you can expand the full action about, excuse me, this background and look at the terms which are coming from higher derivatives. And some of the terms which will come from the dangerous ones are of course the background divided by m Planck to the fourth times h times 4 derivatives of h. And as you know, this will actually necessarily give rise to a ghost. But when you look at the pole now, that ghost will have a mass. From that pole, you can deduce that the ghost will have a mass, which is m Planck squared times a quantity which is bigger than 1, as long as the classical background curvature is less than m Planck squared, as we assumed it should be. And therefore, that state is not really warranted in the effective theory, in this effective field theory, which is defined below m Planck. So the total effective field theory action is what I have written already, but you can have, of course, a bunch of other, well, actually infinite number of other terms, which are combinations of the wild tensor in some power, starting with non-zero 1, covariant derivatives and curvatures constructed in a different variant way. So this is still an effective field theory, which, if focused on the conformal sector, gives you conformal Galileons that I started with. Of course, it requires an infinite number of fine tunings for me to have this theory. They said another way, interesting question that remains after this construction is as to whether there is any UV theory of quantum gravity, coming from string theory or anything else, that for some special UV reasons would have combinations of curvatures in the cubic and quartic order the way they come out in this coset construction. And that obviously the answer to that question is not no. Now, if I nevertheless adopt this approach and ask if there is anything interesting, besides that theory being itself kind of curious, if there is any interesting, for instance, possibly for cosmology, well, there is something. It's along the ways of the Starobinsky thinking, obviously, and that's also natural in this context, the moment you see higher powers of R. But the difference here is that, well, maybe it's not a difference, it's a nuance that I would like to emphasize, is that you can consider cubic or quartic when you focus on the FRW, because as I said, scale factor in FRW is a conformal mode, and we made sure that the conformal mode does not give rise to additional equations with additional derivatives. Therefore, in that conformal mode, there is no other solutions than the ones that kind of match to the initial Cauchy data defined evolution. Of course, that definition is up to you. So here is a toy example in which not all the terms are included, but the cubics are included, the quartics are included, although this can be done in general. And even in the end, even I will drop the quartic term for simplicity or analytic expressions for the solutions. And you can write down the mini superspace action corresponding to this just by substituting conformal mode. It's a lot more complicated, of course, than GR action, but you always are guaranteed to have two-time derivatives. And then the Friedmann equation, which comes out from this, my y denotes Hubble square plus this is spatial curvature just for generality. So that's the y. So it's a Friedmann equation is a polynomial, some kind of polynomial in this variable y. So the cubic and quartic are extra terms, as you know. So if I were to drop them, I would have had y equals to 0. That's an empty space Friedmann equation, which has a Milne solution if k is non-zero for the open universe. But never mind. So this is just modified Friedmann equation without any matter or radiation or anything else. And as you can imagine, it has actually some non-trivial solutions. One of them is given here. This is in fact, this is a de Sitter solution, very similar to the Starobinsky solution. It's contracting and then re-expanding de Sitter solution. But of course, this comes, I should re-emphasize that this comes with tunings of the coefficients of the terms in the action that I had to do in order to have this property of the theory recovering conformal Galileon in that conformal sector. But if that tuning can be justified by any UV considerations, then this becomes, of course, very interesting. But so far, this goes only with that disclaimer that tuning has to be done to have this kind of solutions. All right. So let me conclude. So the goal that I was pursuing is to understand if the Galilean theories or their generalizations can always be part of some bigger tensor theory in which they appear as gauge modes. And we know example of it, that's massive gravity, in which those are longitudinal modes of a massive spin 2. What I didn't describe, but I will summarize here, the story is very interesting in 3 dimensions with conformal Galileons. This again work with the same, my former student, Georgi Tukhashvili. If you follow this procedure in 3 dimensions, well, remarkably, you discover what was known as new massive gravity in 3 dimensions. There was a construction due to Perkshov, Holm, and Townsend And it's a theory which I've written here schematically. It's R plus R square. In fact, it's R, of course, because it's Einstein-Hilbert. And then there is a special combination of R square terms of Ricci scalar and Ricci tensor squared with some special coefficient between the two. And that theory is known to have a massless mode in it and one massive mode. Now, the massless mode has wrong sign kinetic term, but it's argued not to be problematic because there are no local degrees of freedom of a massless spin 2 in 3 dimensions. But the massive mode is entirely healthy, it's just a massive gravity in 3D, and that's the theory. So remarkably, this construction, this Cossack construction, just recovers that theory. So when we started this, I actually maybe a posteriori, I thought I should have guessed it, but I didn't. So, and it recovers that theory in a unitary gauge. Of course, general theory is more general. It has this pi in it and interactions with curvatures and so on and so forth. But that's what it is in 3 dimensions. So this in flavor is similar to what happens in 4 dimensions because we've got well, CC is always there, so I didn't write CC. If you wanted to write CC, or you can always add in. But there is Einstein-Hilbert and then square terms which are Gauss-Bonnet and cubic and quartic, and the Wess-Zumino term with those special combinations, which give you the Galileons. Now, the application to cosmology, as I mentioned, potentially interesting, but as long as it understood that at this point, this is all coming with some fine tunings that one necessarily needs to adapt to have those Galilean theories. So another way how these are derived, these terms are also related to higher dimensional Lovelox. There is a algorithmic limiting procedure, which is outlined in our paper and a number of other papers, so that you start with higher dimensional Lovelox, and those terms algorithmically reduced to these ones in 4 dimensions through some reduction, which is not a physically motivated procedure, but mathematically is well defined. So there is that connection too. So perhaps in future one would try to explore as to what the physical meaning of that reduction is and how that informs us about this effective field theory that I spoke about, whether it provides additional ideas as to why this fine tuning might be justified or not justified. So I will stop here.
Thank you, Gregory. Are there any questions? We've got a few more minutes. Anyone want to raise their virtual hand? Okay, go ahead, Dimitri. No? Gregory, can I ask you then what the constraints are on the cosmological constraints on the conformal Galileon?
That's an excellent question. It depends on the full theory in which they are being considered. So there are, as I mentioned, there are approaches in which Galileon or conformal Galileon is just covariantized, and then the constraints are very severe. Actually, many of them, if not all, are excluded. But this is not that approach. As you see, the full theory that I'm discussing is just some sort of r plus r square plus r cube plus r to the 4th. And so in that theory, these are high dimensional operators, which come suppressed with some high scale. I took that scale to be M Planck here. Well, one can play with that scale because obviously this construction doesn't prescribe what that scale has to be. And if that scale, one can impose all sorts of cosmological and astrophysical constraints on that scale. So that would be a way to ask your question and give some useful answers. So if these are Planckian scales, I don't believe there is any constraints on them. But if you lower that significantly, and you can actually from the point of view of bottom-up approach, you can. Then there will be constraints, of course, with all sorts of considerations, with the early universe mostly.
I think Claudia's got a question.
Thank you very much for the talk. I guess I was wondering how much you can learn from the construction in 3D to export it in 4D, particularly when you're thinking of them as being M-Planck suppressed, and if you can just put all the garbage that would be there in 4D in the 3D construction into goes above the Planck scale as you have.
Hey Claudia, so your
Hey.
question, how much we can learn from the 3D example to think about 4D?
Yes.
It's a little tricky because of the fact that I alluded to. You see, in 3D, somewhat strange sign choices are being made by BHT. See, in 3D, their Einstein-Hilbert term has wrong sign. Has to have wrong sign because for R-squared terms to give you the good massive state, the massless state has to be costly. But again, there is no local degrees of freedom for a massless spin 2, and therefore maybe that's not so bad. Although that minus sign will have manifestation. I mean, you take a point like source, and instead of deficit angle background that any point like source would produce in three-dimensional and gravitational theory, now you have excess of angle because it acts almost like a negative mass in some ways, right? Because the Einstein-Hilbert term has a wrong sign in that theory. Now in 4D, obviously we don't want to do anything like that. So it's so this construction doesn't prescribe what sign you choose, but we choose right sign so that we have Einstein-Hilbert term, a proper Einstein-Hilbert term, a gravitational waves propagating as we want. Once you do that, then you are in a somewhat different mindset that you look at these higher derivative operators as producing extra states which are beyond the cutoff. While in the 3D case, you didn't want that to be beyond the cutoff because the authors wanted to describe massive graviton, which was kind of light or comparable with the, let's say, CC scale that they had. So philosophically, it's somewhat different. So I'm not exactly sure whether it would be one would be useful for the other one. But what I find fascinating is that if you follow this protocol of the coset construction, in both cases you get R plus higher powers of R, and Galileons emerging in both cases as just the conformal modes, and they seem to be special somehow. These terms seem to be special. In 3D, of course, PhD discovered that these are very special combination, and that's why I wrote the theory. So I find very interesting that there are these special combinations in 4D, R cube and R4. I wasn't aware. Maybe there are some people, maybe people are aware that maybe similar combinations appear somewhere. I have no idea. Well, R square, of course, the Gauss-Bonnet, everybody knows, but the R cube and R4, I haven't seen it. So that's something that I would like to understand better in the context of perhaps some UV theory, string theory, whether there's combinations like this in certain string theory constructions which come out naturally for certain reasons. Well, reasons should be related to conformal symmetry, spontaneously broken.
Yes. Yeah, that makes sense.
Okay, thank you, Gregory.
Thank you.
I think we should close now. That on the schedule, there's a short break before restarting. I don't know what time we have to restart. Perhaps a host can actually say.
I think it's 15 minutes.
There's another talk, isn't there? After this workshop, there's the tea time talks at 6 o'clock. So we can't really hang around too much.
Hello. Hello, Anne. Actually, since, yes, the time is strict, we should reconvene, let's say, in 6-7 minutes, not later. Otherwise, we run into the risk of cutting the last talk, because the schedule is to restart at 4:15, and okay, it's almost 4:15. So let's say 5 minutes break, and then it would be better to start again.
Dimitri, do I give? It's Michèle. I don't open my video yet. Do you hear me?
Yes.
So do I give a talk as scheduled, or should we wait, or what? I just
20
joined.
past, I think. At 20 past, we just said.
Yes, at 20 past, but not later.
At 4 and 20 minutes.
It is
Yeah.
45
20.
minutes, including questions. We should start the second and last talk at 5 past 5 at most PM.
Okay, I will also, I can be quicker.
Okay,
Okay.
Thank you very much.
Okay.
Michèle, I'm supposed to be your host, so maybe you can try to share your screen already now.
So first of all, do you see me? I see you.
Yeah.
With
Hi.
the blackboard behind. And share screen. Do you see my screen?
Yes, yes, looks good.
Okay. So I'll stop for now.
Yeah. And to David, the answer is yes.
Sorry, and today?
No, this was a message to David. That's fine.
Okay.
Yeah. So we meet again in 5 minutes.
Okay.
Yeah, why not? Try it now. But are you a co-host already? I'm not sure if I can make you one. Let me check. Yes, you are, David. Try sharing yours. Yeah, looks good. Perfect. Sorry, Rafael, I missed your talk. We had a seminar at the same time.
Are you talking to me?
Yeah, I missed your talk. I'm sorry, but we had a seminar at the same time.
It should be online at some point.
At some point, yeah.
But we will come back to it, hopefully during the workshop, because we are very close to actually getting the full answer. We'll see.
Ah, you mean publishing your paper?
No, not publishing, because we haven't even submitted. But we have the 4 p.m. integrand. Since a while, we are learning how to solve these differential equations, boundary conditions. So we seem to have cracked the code relatively recently for the whole thing.
Hmm.
So we might actually produce not only potentials, but the whole thing, which will be very nice. So
looking forward to it.
Yes, I'm not going to make any claims yet. So we'll see. Is it nice over there too? Here it's beautiful.
Yeah, the sun is out. It's still a bit too cold, but yeah, it's nice.
Oh,
Very
really?
nice.
Oh, my wife just sent me pictures of my kids on the beach, half naked, so it looks like it's warm.
Mm.
I cannot show them because probably it's not.
Well, my kids are playing basketball outside.
They're probably a little older than mine. I'm 7 and 3.
Yes, they are.
Okay. What seminar do you have? Who gave the talk?
Oliver Schlotterer.
Oh, I see. Amplitudes, like
Yeah, string amplitudes. So this last paper he wrote with Henry.
You know, at some point, I always thought about, so what we do with classical, it should have some embedding into some stringy amplitude thing. So this is a big dream of mine, that this idea of how we relate in these radial actions with the amplitude and so on, actually descend from some stringy partition function kind of thing, maybe even from some CFT, and in which we could, perhaps it's like Julio would say, perhaps it's some supergravity, it's not really GR, right? But who cares? If you find a way to connect with stringy calculations, say the periastron advance in supergravity, it will be super beautiful, right? Because then you can see whether you have a non-perturbative answer, which, for example, for the case of Simon's calculation, right, with this no triangle, that you know at one loop there is no periastron, but we think that at two loop that's no longer the case. But there is another conjecture about the radiation reaction, whether that could change the picture, right? And whether you can embed this in an exact solution will be amazing. Unfortunately, I never understand a single word of what these guys do. Literally, I get lost in the second slide. So maybe one day we can organize it. This ambi-twist or blah, blah, I have no freaking clue what that is, right?
Yeah, I don't see a connection really at this point.
Hi, Rafael, may I ask you a question? Kostas Papadopoulos here.
I don't see you. I hear you, but I don't see you.
Ah, okay. You would like to see me as well. Okay.
No, it doesn't. I mean, I don't know who you are. Hi.
Okay. Hi. Okay.
Oh, hi. Okay. Now I see.
So I see in your paper, which is about this bound state problem.
Yeah.
So there is a case where the masses are equal and they have a circular orbit. Okay?
No, any orbit. And the masses don't have to be equal.
Yes, but okay, let's stay for the circular orbit, okay? Yeah. Is this, because you know, there is a paper by Lick-Blanchet and later by Foucault that they claim that the gravitational potential in that case, in the ultra-relativistic limit, it takes a factor of gamma to some power.
I never seen this. Who are you referring to?
So it's a paper by Foucault. Okay, I can tell you, but the point is the following. I mean, in your paper, you give some expression for the potential, but I'm not quite sure. So if you take, let's say, the first post-Minkowskian approximation of the ultra-relativistic limit, do you find that there is
that, right? Because if you are bound, right? If you cut in post-Minkowskian, then you're bound in post-Newtonian in a sense, right? So if you give an orbit, right, they are not independent expansion parameters. If you start going very quickly, so you're saying you fix the energy, you assume some circular orbit. Is that what you're doing? And you're computing the binding energy, say. Is that what you're doing? As a function of what, of the frequency. And then you take what?
The distance.
Closer orbits?
Yeah. Let's say the distance, okay? Let's say the gravitational potential.
I don't want to use gauge-dependent quantities, but okay.
Yes. In any case, so do you think that is it possible that you get the kind of strong gravity in a sense in this situation? I mean, because of the gamma factor.
Well, the gammas are there for us, right? It's like this boost factor because it resounds a lot of the post-Newtonian contributions, right? So this Hamiltonian, if you want. But as it has been discussed in the literature as well, if you look at the angle and you look at the high energy limit, which has a well-defined, there's this logarithmic singularity, and then there's this radiation reaction effects that cancel out. In fact, it's very interesting, we mentioned this. The log of m in the 3 p.m., it becomes a polynomial at 4 p.m. And we seem to be finding very complicated functions for the full sub-region, the dissipative region. So it might be that we actually, that singularity at 4 p.m. in the dissipation, it looks really nasty in 4 p.m. So,
but let's say in one.
Okay, guys, I'm sorry, I have to stop your discussion now because we want to continue with the meeting. And the first speaker this afternoon after tea time, I think it was called, is Michèle Levi from the Niels Bohr Institute in Copenhagen. Michèle, are you there? Michèle? I hope she didn't misunderstand. But
yes, I am. Yes,
okay, sorry. Yeah, can you go ahead, share your screen?
Yes.
And the stage is yours. Michèle is going to speak on gravity at all scales from QFT strategies. Please.
Okay, so thank you for the invitation, and it would be interesting to see how the online interaction in the coming weeks would work. So I will talk about my line of work, which I've been building for some years already. And little by little, it's been expanding also in techniques and in scope. But it's all about applying effective field theories in post-Newtonian gravity, and then using QFT methods, or also seeing what are the, if there are QFT insights from this kind of study. So I won't show again the gravitational wave signal. I assume that at this point you've seen it at least 10 times since the beginning of the conference and other times. But we all know what is the theoretical form of the gravitational wave signal, and that the inspiral phase of the signal constitutes the major portion of the theoretical signal, although not always actually detected if the event is too loud, is too abrupt. We won't see much of the inspiral, but in principle, all of the signal contains a large portion of post-Newtonian theory. And this portion is crucial because there are bits of physics that we can only infer by learning the physics that goes on there, in particular about the constituents, the individual constituents of the binary, about scenarios of how this binary formed, for example. And so I'm in general interested in every independent methodology that can inform me, about post-Newtonian theory. In principle, at the moment, gravitational waveforms, which are targeting equal mass, at the moment, that's the detectors that we have for equal mass binaries, they only use a post-Newtonian theory and a numerical relativity. Actually, perturbation theory is only used as some kind of an academic corroboration. It's not really needed in order to cover the end of the event. But in any case, we can see from this kind of phase space here that is drawn in this plot that at the end of the gravitational wave event, when we have one merged object, one remnant object, then we can use this approximation, this way of thinking that we actually have a test particle in the background of another particle as we try to describe the settling of the space-time, of the perturbed space-time into the final, usually Kerr black hole. Now, just a word of clarification regarding a frequently asked question. So we are heading towards an increasing influx of real-world gravitational wave data, and that means that we also want to have a theoretical gravitational wave data, which will be as of high quality as possible, and will contain the most physical effect that we can. So pin gravity is a key theoretical ingredient for that. And so usually a frequently asked question, I just want to clarify. So my work is all about effective field theory of post-Newtonian gravity, which is an independent methodology in order to produce results in post-Newtonian theory. Any other methodology that informs post-Newtonian theory is as good. Recently, there emerged some methods that use or recycle, or some may say abuse, results from cell-force theory, which means that we are using results that are obtained for this ratio of masses, and using the effective one-body formalism, we are mapping them to post-Newtonian theory. So the word of clarification is that while my effective field theory is effective in that it's suppressing small scales in a systematic manner in scales of a small parameter, which is the non-relativistic velocity, which characterizes this the inspiral phase. The effective one-body is effective in that it's mapping a two-body problem to a one-body problem. That was the great idea of Buonanno and Damour to generalize the idea that we all know so well from classical mechanics to general relativity. And by doing that, to map results of post-Newtonian theory to cell-force theory. So recently, this idea was kind of used and recycled to use it in the other way instead of mapping post-Newtonian theory results to perturbation theory results. Actually, known results from self-force theory were used in order to deduce new results of a post-Newtonian theory. By using this kind of methodology, we actually lose an important consistency check of results in post-Newtonian theory, which are usually to take the limit of a test particle. And also another thing to notice is that there's also a limit to how much self-force theory results are out there. In fact, it's as torturous and rigorous and laborious to get a high order results in self-force theory. So basically it's a conservation where what we are doing is transferring the problem of hard work from post-Newtonian theory to self-force theory. So I don't see any particular advantage to doing that instead of coming up with some independent methodology that contributes directly to deriving results in post-Newtonian theory. Now, beyond the fact that obviously these results are needed for real-world data, there is very interesting underlying science. In particular, we don't completely understand why, but we know. Sorry.
I think that was nothing. Go on.
Am I heard?
Yes, everything is fine. I think that was just an error by one of the participants. Okay. Please go on.
Okay. Okay. So we know that the results in post-Newtonian theory, in fact, in many different contexts of computing high dimensions of generally in large extra dimensions and whatnot, in very low approximation of post-Newtonian gravity, we already get results which imitate in a very good way already results of strong gravity. So in many ways, PM gravity already informs on strong gravity in a way which we cannot fully understand yet. And in general, this study deepens the understanding of the analogies between quantum field theories to gravity, even between quantum field theory to classical gravity, even just in terms of techniques, but also in terms of later, as you will see, now we're getting to a point that we're actually trying to understand if things that are known as a problem, as a fundamental problem in QFT, are they actually a problem at the classical level? And it's just that before now we weren't able to reach to this level of computations in classical gravity, but now we are. So actually we may shed new light. So just a general picture of the state of the art of for generic compact binary dynamics. So in general, all of the computations that I'm interested at are trying to give generic results for black holes and neutron stars. So not only for black holes. And in general, there are two parameters which are important in order to set the difficulty of to say what is the difficulty of the computation. And that is true also if you're doing a post-Newtonian or post-Minkowskian, or I mean, there are easier ways to compute or harder ways to compute, but nevertheless, the indices that will matter are the index n, which will designate the highest n-loop graph that one encounters in the sector, and the index L, which will designate the highest spin. If it's in the quantum context, it will be just the number of multiples of halves of spin. If it's in the classical context, just it means the highest multiple moment that will be included in the sector. These two parameters taken together will fix how difficult it is to tackle the sector. And in general, each sector will contribute in the PN context will contribute at an order of n plus L plus the parity of L over 2. So it's the sum of the two, which constitutes the overall difficulty. And also we note already at this point that we already can take notice that there is some kind of an area which corresponds to gravitational Compton scattering. When we say gravitational Compton scattering, I mean the scattering, which already requires a 4-particle scattering, 4-particle amplitude. So as of the point that we are starting to consider nonlinear interactions, there is actually a correspondence between sectors of quantum spin with the spins larger than 3/2 to classical sectors with s to the power of L. And so we don't know, but we start to see already classically that weird things start to happen, and I'll get to that really in the end. We expect weird things to happen, and we don't know if we will also see them at classical level, if we will, from which spin we will see them. Let's say that spin to the third cubic in spin is the first sector where we should first take notice, because of the various classical features that we see. Now, in general things that can be said also about the state of the art, there are general trends that can be, at least for all the sectors that are known so far, which are the ones that are covered in this table. So the legend here is that 2 pluses, it's not helicity notation. 2 pluses means that the sector is fully done and fully verified. 1 plus means that the sector was only partially approached or only approached by a single group, so it has to be cross-checked. These computations are obviously very complicated, so it's not enough for one group or one collaboration or one methodology to perform them. And we see general trends, and the general trends are that in general, an index L, which is even, is always easier to handle than an odd L. Also, in particular, there in the easier case where L equals 0, in particular in the non-spinning sector, there is also another a greater ease that happens when the index n is odd. At 4pn, the current state of affairs is that at 4pn, as you can see from the table, at 4pn, all sectors are fully verified except one sector, which correspond to the entries 2, 2, so next to leading order spin squared, which was derived within my methodology and was not, to the best of my knowledge, confirmed yet by any other method. And apart from that, essentially, I would say that the community moved on, or most of the groups which are engaged with really pushing the state of the art, really the precision frontier, are working on attacking the 4.5pn and the 5pn, which are approached at several degrees, and where no sector is currently fully done and verified. And I should note that that's actually relevant from very low orders, but one of the things that makes it a challenge at these high orders is that as of 2pn order, the UV dependence is needed to complete every accuracy. So, and what I mean by UV dependence is the basically finite size effects already start to play a role. So we have like these black boxes that we carry in our expressions, the Wilson coefficients that I'll show you immediately. And so we also need to handle them in order to complete every accuracy above at 2pn and above. So we start then by considering, in my methodology, we just start by considering in general an effective field theory of extended gravitating objects, and I won't talk about the whole formalism, but in general, the point is to consider how we move from a fully gravitational action to an effective action where we just stay with the bulk action, the gravitational bulk action of the weaker, of the lower momentum field modes. And we complement that by adding a set of infinite operators, which are localized on the world line, on the trajectory on which the compact object is moving. And therefore, the big challenge is at the first level is to be able to say what is this point particle action. So in a systematic manner, to be able to enumerate the operators and the corresponding Wilson coefficients that will precede them that will encapsulate the UV physics that is being suppressed. So as far as the gravitational part should be handled, we can, of course, experiment with any of our favorite chosen gravity theory. So, we start by doing it for Einstein-Hilbert action. So, we use the standard convenient gauge, fully harmonic gauge, and we use a d-dimensional dependence Newton constant because basically from two loop and on, we should be kind of conscious of really conscious of dependence in D because we are regularizing integrals with the dimensional regularization and so on. So we should keep track of these parameters along the way. And virtually in all of the computations that have applied IPhT in post-Newtonian gravity, there was one simplification that was really helpful, and that was that when we are talking about the non-relativistic context, we can think about reducing the time dimension compared to the spatial dimension. So we do something like a Kaluza-Klein reduction, and that makes our life much easier. In principle, all the problem boils down to a 3D. All our integrals are 3D, in 3D momenta, with propagators, which are just delta functions in time. And also the components of the metric decouple very nicely. So in principle, when we are restricted to the case where non-spinning objects are considered, I would say it's fairly straightforward. It's fairly, it's more of a loop. It's more of a loop technique problem to push forward with the computations, the precision frontier also in gravity. However, so I mean, to the point that in fact, up to 5 p.m., we don't even have to think about anything beyond the point mass in order to say what is the point particle action. So it's very simple, and even at 5 p.m., we don't have to think a lot more. The situation changes dramatically when we want to start considering spin. So there are very good works that were done already in the 70s, considering spin in flat space-time and in curved space-time. And in general, already from there, we saw the definitions of two generalized velocity, the forward velocity and the generalized angular velocity. Just using basic symmetries that are just valid already in the point mass case, we can already infer the general form of the non-minimal coupling part of the effective action. So that's something that we could have seen already in these very old works from the 70s. I would say the new input that we started to realize was that, first of all, we define the spin as the conjugate momenta to this generalized angular velocity. And in fact, we really have to consider it as a further particle degree of freedom for all purposes and reasons, and be very, very careful about it, about how we treat it in gauging and the relationship between the spin and the tetrad gauging, and the way that we derive equations of motion, various equations of motion from our results. So in principle, a very central point was to understand that we should really consider the spin as an extra particle degree of freedom. And it actually meshes well with the point of view, with the IPhT point of view, in the sense that we consider the spin as a classical source on the word line, just like we consider the point mass, for example. So this form that we already saw from the 70s of the non-minimal coupling of the minimal coupling of the action, in fact, assumes an initial covariant gauge, which means that when we use this mathematical construct of a tetrad, we choose that the temporal component of the tetrad is parallel to the linear momentum. and the spin is orthogonal to the linear momentum. So there's an implicit assumption here. If actually one works out the logic of what we see here, that's what we find out. That was something that was put forward for the first time many years ago at 59. So what was the challenge when I approached my work? There were basically two challenges to tackle. The first one was to understand better what is the meaning of this term that represents the rotation, the fact that we now have a spin, but still without considering finite size effects, just minimal coupling. So the problem is there is a conceptual problem, and the conceptual problem is that the relativistic spin has a minimal finite measure, which is the lower bound is given by the size of the spin over the mass. And the fact that it's an extended object, it clashes with how we want to describe it within this treatment, which is a point particle viewpoint. That's the IPhT viewpoint. So we have to be able to put the two together. And due to the fact that it has an extended measure, this spinning object, in general, a relativistic spinning object, in general, even without the IPhT, there was a lot of confusion in the literature regarding different choices of various people along in a long history of approaching such corrections with spin, of how do you choose the representative point within this extended object which you track, the evolution of which you track. So the first challenge we wanted to tackle is to introduce a gauge freedom in the choice of rotational variables in a way that will make sense in all the messy literature that was there before, that really explains to us and to everyone what's the meaning of the different choices and how to relate them. That was one fundamental issue that had to be tackled really from the get-go, because this is still minimal coupling. And the other thing is to fix the non-minimal coupling. So after that, we have less trivial couplings of the spin coupled to now Riemann and covariant derivatives. And can we constrain them in a very strict way that will inform us at least, we'll tackle order by order, at least the orders that we need to tackle. So these were the challenges that we tackled. So the first idea was, in fact, the first realization was, to me, it always reminds me of the Stuckelberg trick, and that's why I like to put here the picture of Stuckelberg, because it's very similar to the Stuckelberg action, where he actually realized that there was an implicit choice of gauge, and in fact, if you release this choice of gauge, there is a greater freedom of gauge, and so actually we kind of did a similar in spirit exercise, where in fact we realized that the freedom, our hidden freedom, lies in the choice of the temporal component of the tetrad. And in fact, if we apply some legal transformation on the temporal component of the tetrad, we exactly can get to some kind of a generalized form of what could be the choices, the gauge choices for this tetrad that designates the generalized angular velocity and the spin variable that we are using to describe our rotation. And by having this generalization, we could now see how we recognize, how we identify the different choices that were previously used in the literature and not really fully understood. So that was one thing that we did. And so in fact, what it means is that, as I explained, since we're talking about the fact that we have an extended object, it just means that we are literally just moving our center of spin with respect to some previous center to a new center, which is orthogonal to the direction of motion. So if we do that generally, we find that an extra term in the action appears. So this was when there was an implicit choice of the covariant gauge, but when we release this gauge and we switch to another choice of a gauge, we actually find that in general we have this expression. So we see that there is an extra term with a covariant derivative of momentum momentum. It contributes to finite size effects, but it carries no information about the UV structure of the object. So inherently, it doesn't depend on any UV physics that goes on in the spinning object. It just tells us that the basic fact that the relativistic spinning object has to have a finite measure, a finite extended measure. And this term contributes would manifest in really from the leading order affecting spin. It would affect all sectors in spin. And essentially this amounts to the Thomas precision, this term. And also later on, actually, when people recently approached this problem in trying to do it with the amplitudes methods, they recovered it they called it in other names like Hilbert space matching, but essentially they found out that they had to do something which is exactly equivalent to that in order to really fall on correct results. So we have a way to transform in general from the initial variable to any chosen spin variable. And so that was the first challenge that we tackled in the theory. Now, specifically, we found that it would be very advantageous to specify, anyway, when we compute anything, even if we compute some gauge invariant quantity, we compute it through choosing some gauge. So we should specify a gauge. And we find it very advantageous to use the generalization that we found to the rotational variables. We could find what is the generalization of a canonical gauge to curved space-time. And here are some of the obvious reasons that we find in order to use it. Why to use it? I mean, because we always want gauge invariant quantities and observable quantities, but there are clear advantages to specifically using this gauge in this formalism. So specifically, as we show in our work, this allows to disentangle these degrees of freedom. This is in fact the only choice that we could see that allows to disentangle degrees of freedom in an IPhT treatment and land on a well-defined effective action. That's one thing. The second thing is that once you then land on an effective action and a well-defined effective action, the procedure to get to a Hamiltonian is basically now becomes completely equivalent to the non-spinning case, apart from the fact that you will have spins and you will have the higher derivative of spins that you will have to treat in a certain way. But in principle, the procedures that we apply are similar: reduction of time derivatives and then a standard Legendre transform, and there's nothing that is left ambiguous. That's the second reason. A third reason is that a Hamiltonian is an object which is essential for the effective one-body framework, which is currently the unique framework which generates gravitational waveforms. A fourth reason is that within this framework, it's then very direct and simple. It gives us a very direct and simple way to derive physical equations of motion for both the position and the spin. It also enables the stringent consistency check that I'm aware of the results for non-restricted cases. I mean, without still restricting to black hole or aligned spins, or so it enables the stringent consistency check of the results by checking the global Poincare invariance if they satisfy the expected Poincare algebra. And also something that is more of a fundamental interest is that this treatment, as I already hinted before, with the mention to the connection to the Hilbert space matching, it's the most natural classical treatment to be promoted and confronted with QFT. It's the closest one to be confronted with some analogous QFT treatment. So that's all that is regarding the gauge choice. Now, as to the second problem which we had, which was to say something more informative about the non-minimal coupling part of the action. So I would say that the key here, which we identified already and we spelled out in much detail in a paper from 2015, here the key was to realize that the key object to use in order to construct everything is to use a classical spin vector, which is similar to a Pauli-Lubansky vector. So once we do that, we naturally have something which has definite parity. So that's one advantage, because parity invariance is a symmetry that plays a role in how to constrain our action. And the other thing is that it naturally, just by definition, the Pauli-Lubansky vector is orthogonal to the linear momentum. And that means that in what we call the body fixed frame, that's naturally an SO3 entity. So it means that we want to handle with all the objects that we will have essentially would be SO3 tensor, SO3 EREPs. So once we realize that this is the key object in our construction, first of all, note that it immediately resonates with the description that came actually not much later in 2017 from an SO3 spin vector to these SU2 spinners in the massive spinor helicity of Arkani Hamed and the collaborators. Specifically, what we show in detail, we work out all the details, we show that in fact, our non-minimal couplings, they are just a direct product of the spin vector, much similar to the massive spinor helicity, which takes these direct products of SU2 spinners. And then the way to see what are the couplings is very straightforward, because according to the parity, the overall parity of this direct product of the spin vectors, we know whether to couple it to an odd parity or even parity component of the curvature field. And so we find that at the first approximation, which is the first approximation is linear in the curvature, that there is an infinite set of couplings of spin to linear in curvature that has this form to them. And if we pull out and they are preceded by new Wilson coefficients, which correspond to log numbers or quadrupolar deformation coefficients. And if we pull out the three first terms from this infinite series, we already get terms that are needed to complete our current sought after precision frontier at 5 p.m. So we need the quadrupole, the octupole, and the hexadecapole in order to complete the 5 p.m. It's not clear yet if it's the whole story, but it's at least the beginning of the story is to have these couplings which are linear in the curvature. So that was the second thing that we
Sorry, Michèle, just to warn you, you only have 12 minutes left, right? Just to
okay. Okay. So I will be a bit quicker. So as you could see in the state-of-the-art table, the challenge proceeds in two different directions: the direction of the parameter n, which talks about the high loops, and the direction of the high L's, which talks about high spins. So the first thing was to, in particular, I wanted to also push spins. Sorry, I also wanted to push spins to higher loops, and in particular, I went to 3-loop recently, and so 3 loops were already obviously tackled in the non-spinning sector. However, when we treated it, I saw important things that I didn't see mentioned anywhere before. Now, what you see here is what I draw as the topologies of my graph. So basically, the graphs are only what you see between these two between these two vertical lines. So these are the gravitons that constitute the graph. It's only what's between these two solid vertical lines. And so we have the single topology of a one graviton exchange. Then when we go to one loop, we will have nonlinear couplings on the word line, and we will have a bulk nonlinear interaction, and so on and so forth. What's interesting to say is that we can adopt two perspectives when we do this analysis, and both of them we'll have to keep in mind in order to gain an insight on the things that we get. So first of all, we can easily make a pretty trivial change of variables that will basically tell us that all of the graphs that we will see ever can be represented as a loop integral that is nested in a trivial Fourier integral, which means that it's only a transfer, basically a transfer momentum and a loop graph that is between 2 points. So that's basically the meaning of this analogy that we see here depicted in this picture, is that we can move from the word line picture and use this 2-point quantum picture in order to tackle the graphs. And that's a useful perspective practically, because we realize that if we encounter difficult integrals, we can look them up in a QFT multi-loop textbook, look for n-loop master integrals, apply IBP, integration by parts techniques that are known very well from a multi-loop QFT. And we included all of that in a code that I devised and is continually developed in order to do this kind of computation. But so still keeping this perspective, the important thing that will designate to us what is the level of difficulty of handling this graph is to use the following definition, is that basically at each level, we would actually identify that there is a basis of typical integrals that appears. And a topology is at rank R when R basic n-loop integral types form its n-loop integral. So a 3-loop level, for example, a 3-loop integral can need only one basis integral. So that would be a rank 1, a rank 1 topology. Up to a 3-rank topology, this would be the most complicated. So if we keep it still simple, a 2-loop level, for example, that's the only graph which is a 2-rank. So which means that it's more complicated to evaluate than the other ones here. It's a 2-rank, which means that it's the first one that actually needs integration by parts, because it has, you can express the integral only as a sum, as some kind of a sum that you have to work in order to get to of 2 other basic types of integrals. Now, when we proceed, we want to actually keep also the wordline perspective. And that is, for that, we kind of bear in mind that we want to use this definition that tells us what is the loop order in the wordline perspective. Even basically, the loop order in the wordline perspective is basically just to see how many internal interactions we have. If all the internal interactions are saturated, this is the highest loop that we can have in a topology. In particular, this constitutes all the topologies that enter at OG to the order of G to the 4th. But if we apply this definition, and we can also see it very easily from the graphs, only these 2 topologies here and these 10 topologies here are genuine 3-loop graphs. With the meaning that the nonlinearity comes purely from bulk interactions. And that makes a difference, as we find out. It makes a difference because the features that we encounter, the level of effects that we get from the integrals only come from these loop integrals, which are highest in the wordline picture. So, so that's why it was important for me to highlight to you these 2 definitions that were not introduced before and were very informative on the level of complexity of the computation and on what results we expect from the different graphs. Now, in particular, we are attacking, for example, I'm just really sampling one sector that I'm attacking at the moment, which is to complete the next to leading order quadratic in spin. So if we consider only the linear in curvature couplings first, this is work that was started with the Andrew McLeod and Matt von Hippel, and is now continued with Jung-Woo Kim and Zhu Yin from Queen Mary and from Uppsala, and it's in preparation. So this is the graph distribution. Of course, it's horrendous. It's a huge amount of work, a total of 1,024 graphs that we have to tackle. But fortunately, once we exercise this distinction that was exemplified in these definitions that I gave, we see that actually not a lot of these graphs are actually ones that require IBP or are genuine higher loops. So it's a lot of work, but we can now identify where the difficulty lies. Now there's a question, do we have more contributions beyond linear in curvature? So in fact, in quadratic in spin, we actually have, and we'll see that later. Yes, we have actually another contribution that enters a G-square and comes from quadratic in curvature contribution. So in principle, now we're working, we have worked and we continually still work to upgrade just the level of efficiency and really rapidity of our codes. So building on the original IPhT of PNG code, we're handling the higher rank graphs using IBP. So as you can see here, there are in fact not a lot of this 1000 whatever that require IBP, but still they require much more work. So we have to do it efficiently. And the main improvements, in fact, now we've put focus on the first one, which becomes very central because we're dealing with spin. So there's a lot of projection. So is to just upgrade the projection method for integrate numerators because they're very high with spins, as high as rank 8. Beyond the fact that we upgrade IBP from doing it by what we call by hand, although we did it with the code, at 2-loop it was sufficient, but here we really had to resort to algorithmic IBP. We did our own variation of Laporte algorithm.
Michèle, you only have 3 more minutes. 3 more minutes.
I'll be super
I'm sorry.
quick. So what are the curious findings that we find at 3-loop? I mean, which are uniquely kind of related to the high loop level. So first of all, as I alluded to before, only 3-loop graphs in the wordline picture. So that's why we want to keep the wordline picture perspective, give rise to novel features, these interesting features of pairs, logs, and transcendental numbers, of which only the rank 3 topologies, so, and this is, the rank 3 topologies are characterized by using the quantum 2-point picture. So only rank 3 topologies, which is a subset, in fact, of 3-loop graphs, give rise to transcendental numbers. And in fact, I mean, once we kind of look into it, it was very interesting to see that, in fact, we can really see exactly where these transcendental numbers arise from, because in the usual quantum context, they arise as the first loop corrections. And in our classical computations, the first time that we encounter what seems to be purely quantum corrections occurs at 2-loop, because we have contact interaction terms of purely short distance contributions. So at 2-loop level, they vanish. We say that they vanish classically, but then at the 1-loop order, they in fact introduce these transcendental numbers. So, and another thing which is still a puzzle is that the appearance of all special features at the total 3-loop results seems to occur only in odd in spin sectors. So as far as all that is known until today, in all known non-spinning sectors or in quadratic and spin sectors, all these special features seem to disappear from the total result. We don't know why, but they disappear, as opposed to the odd in spin where they're still hanging there. So we don't really understand that. That's just, we can conjecture why, we can try to understand why, but at the moment it's just something to notice. Now, another thing that, as I said, we are interested to inquire is what happens in nonlinear higher spin sectors. And in particular, we would like to eventually get to say, if we understand something from the correspondence between classical S to the power of L, quantum spin L over 2, if we can get insight on the Compton scattering of graviton and massive higher spin, of spin larger than 5 over 2. And in fact, we indeed get some wacky features. So that's a work that is really a line of works. It's far from being complete. So it's been done by me and students, and Fei Tang, who is a postdoc, and Roger Morales, a student now. So there is the simple part, which is like graphs with, with elementary wordline graviton coupling. So that's the very easy part. But then we have some wordline graviton couplings, which are quite intricate and subtle, introducing some mixing of original multiple couplings. And also on top of that, we'll have contributions which are quadratic in the curvature. I already alluded to that in the quadratic in spin. So in fact, if we continue our extension of the minimal coupling, of the non-linear coupling part of the action, beyond 5pn, because that's the point where it actually starts to become relevant, we would see that the even in spin sectors actually enter at 5pn. So we would have actually contribution at quadratic in spin and at quartic in spin that enter in the relevant sectors that I'm interested at. So we'll have further new Wilson coefficients, which to the best of my knowledge, I really try to investigate this with all my people in the gravitational wave community. These were not at all considered in the past.
Michèle, could you wrap up? I'm sorry,
your
time is up. Your time is up.
Yeah.
I'm sorry.
I will conclude very fast. Basically, we don't even know if some of them are on shell yet. We don't know it yet. So in general, I'll just say that we have curious findings already at this next to leading order higher in spin sectors, and they're still under investigation. And really, we really have to proceed a lot in order to see what they mean. And I'll just conclude. So thank you for your patience. I'll just conclude by saying that in general, this framework has achieved real-world scalability. It is a self-contained framework. It allows direct derivation of useful and physical quantities. So useful in the sense that they're not necessarily physical, but useful for a construction of gravitational waveforms. And it also allows for the strongest self-consistency check that I'm aware of. The precision frontier is being pushed with this methodology to 5PN order at the moment. There is a continuous development of public tools. And we are also hoping to get a lot of fundamental lessons from these inquiries. In particular, we learn about gravity in general, about strong gravity. We see new features, curious, weird features that we don't fully understand yet in nonlinear higher spin sectors. And we hope to get a possible insight for the graviton Compton amplitude with higher spin. So thank you very much for your patience.
Thank you, Michèle, for a great talk. We're running low on time, so maybe at most 1 or 2 questions.
No, there is no time for question. I'm very sorry about that, but we have to start immediately with the last speaker.
Okay, that's what the boss says. So we have to move the questions then to the discussion session next week. So please, then the next speaker is David Kosower from CEA-Saclay, and he will speak about amplitudes from waveforms. No, from amplitudes to waveforms.
Thank you, Jan, and thanks to the organizers for the opportunity to speak at this virtual conference. Thanks also for them to persevering and organizing it in spite of the fact that I believe all of us, certainly I would have much preferred to be walking out after the colloquium this evening onto the streets of Florence than where I am. I'm going to review some work that was done with Donal O'Connell and with his then student Ben Mabey, and also talk about ongoing work with 2 SAGEX students, Andrea Cristofoli and Ricardo Gonzo. And Ricardo in particular is, as I understand it, going to be finishing his PhD this winter. So I encourage you to keep an eye out for his postdoctoral applications. Both of them are, of course, very talented students. So we're all, let's see, there we go. We're all interested this week focusing on the radiation from binary mergers, in particular, ultimately in extracting waveforms. 3 phases you've heard about before. You'll continue to hear about them: inspiral, merger, ring down. Everything that I'm going to say is going to be ultimately focused on the inspiral phase and in the context of perturbation theory. We want these templates both for the detection of signal and for the measurement of parameters once the signals have been fished out of the noisy background. Now, general relativists, as we've already heard in talks by Bonanno, Pretorius Damour, Blanchet and Pfeiffer, and as we'll hear also, I think, from Jan Steinhoff and Helvi Vitek, have been doing this very successfully for many decades. And indeed, there have also been applications of quantum field theory in the guise of effective field theory that were pioneered a decade and a half ago by Walter Goldberger and Ira Rothstein, that we've heard talks today by Rafael Porto and just the previous talk by Michèle Levi. And we'll hear more from Riccardo Storani and from Ira himself later on in the week. And the excitement, of course, is driven both by the observations that are continuing to come in and by the fact that they call for more precision, so wanting to go to higher order, wanting more spin information, some of which we just heard about, and also just lots more numerical templates. And even though there's been a lot of success, it's also a very challenging project, which is why some of us have been interested in trying to think about a completely different approach to the subject, one based in quantum scattering amplitudes. Now, this is not an obvious thing to think about because ultimately we're interested in a bound state classical problem. And so how quantum scattering amplitudes, starting out at least above threshold, can help may not be so obvious. First of all, we're kind of riding on 3 decades of innovation in the technology of these calculations. We've learned how to do calculations based on the fundamental physical principles, factorization and unitarity, and to do them in manifestly gauge invariant ways, to calculate only what's really needed for physical quantities. We've learned how to separate spin from integration in a very natural way. And in fact, the whole program, in a sense, has been a rethinking of quantum field theory and completely banishing the unphysical aspects of Feynman diagrams. And indeed, most frontier calculations in QCD today use at least some of the technologies that have been developed, and the ones at high multiplicity for the LHC make use of many of them. And maybe the most direct thing that one can say here as a justification or as a motivation is that they've also taught us how to organize calculations and how to reveal a new structure. And certainly the theme over time has been to do frontier calculations, understand new structure, understand how that can be used to simplify higher orders or further calculations. Now, in the context of on-shell amplitudes, the kind of master equation is where we write a loop amplitude as a sum over some set of master integrals of a product of tree amplitudes, generally evaluated at complex momentum, multiplied by those master integrals. And that's information, for example, is all contained in the product of tree amplitude. Unitarity is embedded in the integral. So that's what that means concretely. Now, one of the examples of structural advantages that have been uncovered by work in amplitudes is that of the so-called double copy. And that's the observation that in a certain sense, gravity is the square of Yang-Mills, and that allows you to greatly simplify calculations in gravity. And this, in quantum field theory, is an echo of a much earlier relation, the Kawhi-Llewellyn-Tai relation for on-shell string amplitudes. So if we go back to the 1960s, and we look at DeWitt's papers, we find that there's actually an infinite number of vertices in gravity, and these vertices, even in optimal gauge choice, are complicated, and they get increasingly more complicated as one goes to higher points. And those higher points are required if one is going to higher orders in the perturbative expansion. And yet, if we look at the on-shell double copy, if we look at the simplest case of that at the 3-point amplitude, here again, this is all in terms of complex momenta, and these angle objects are so-called spinor products. Think of them as square root of Lorentz products if you don't know what they are. Then at this level, gravity, once one has stripped the coupling, is literally the square of the Yang-Mills amplitude. And this simplification continues for on-shell amplitudes to higher points, and it's very well understood at tree level, and also for the construction of integrands. Now, a lot of the traditional work and some of the work we're hearing about here is in the context of the post-Newtonian approximation. We're going to be thinking about just the plain perturbative expansion just in G and keeping things fully relativistic. The other thing that's perhaps a little bit more traditional is to separate out the potentials and to be thinking about conservative and dissipative or radiation reaction separately. It's more natural if you're coming from a field theory point of view to consider them both together, and perhaps to more make a distinction between scattering and radiative observables. So if one thinks about amplitudes-based approaches, there's different ways of attacking this problem. In Steve Byrne's talk yesterday, we heard about one where one matches to an effective field theory. And so the idea is from the effective field theory to derive, from the general IPhT to derive coefficients for the potential, also to derive an amplitude, to match that amplitude to one that is built using the double copying, using modern amplitudes techniques, ultimately from general relativity. And then by that route to extract the actual values for these coefficients in the real world. Of course, one could generalize this to extensions of gravity too, if one were interested in this. One can look at analyzing amplitudes. One can take Eikenal approaches, which I understand we'll hear a little bit more about from Rodolfo Russo a little bit later this week. There are worldline approaches, which our chairman has worked on. And there's also the approach that my collaborators and I have focused on, namely looking at classical limits of quantum observables. And in one sense, that's can be thought of as the scenic route. Although in another sense, as I'll try and come back to at the very end, it can also be thought of as the most direct route. So the basic idea is to pick well-defined observables in the quantum theory that are also relevant classically. And we express them in terms of scattering amplitudes in the quantum theory. And then we understand how to take the classical limit efficiently. Now, scenery suggests perhaps tourism, but in fact, we now, thanks to a recent pair of papers from Enrico Herman, Julio Parra Martinez, Michael Ruf, and Mao Tseng, are now also for professionals as well as tourists, and I'll show you a snapshot of one of their results in a few minutes. So the basic setup is that, at least in the initial case, is to start by scattering two massive particles, and in the spirit of the times, I've decorated them with the appropriate spikes. We scatter these, and then we want to examine some observables. So one example that we looked at is the change in momentum, which in the language of classical field theory is called the impulse of one of these particles, and also at the total radiated momentum. And we'll come back to how we look at the wave amplitude directly a little bit later. One thing we have to keep in mind is that we all love scattering amplitudes, but they're not the final goal or physically meaningful on their own. And I'll come back and make a few more comments in that direction in a few minutes. First thing we have to understand is how to build our states that we're going to scatter. And again, we're going to work here entirely in the above threshold in the scattering domain. And of course, for some observables, Rafael has shown us how to go from the scattering domain to bound states. And it'll be interesting to generalize some of those ideas to other observables. So we don't want the plane wave states that we're used to dealing with in quantum field theory, for example, for LHC calculations in QCD. We want to have something that will reduce to point particles with localized positions and momentum. So we're going to build a wave function, which I'll denote with a little phi of momentum, and we'll integrate that over on-shell phase space. We're going to build this out of plane wave states with two particle plane wave states in this case, which are just products of one particle plane wave states. There's the on-shell phase space measure, which I'll abbreviate by a capital phi. And there's also a phase factor, which incorporates the fact that we're going to have an impact parameter for the scattering. And the various hats here clean up the 2 pi's, so we don't have to write and stare at a lot of 2 pi's here. So we want to take the classical limit, and to do that, we need to take h bars to 0. So of course, the first thing we need to do is to restore h bar. On the other hand, we're still going to be doing things relativistically, so we're going to keep c equals 1. If you want to put it back, just do more dimensional analysis. And dimensional analysis is indeed the way that we put the h bars back in. One can do this in a way that keeps the dimension of the states the same and the dimensions of the amplitudes the same as what we're used to, appropriate powers of the mass dimension. The only difference now is that inverse length is no longer the same thing as mass. And the net effect is both of the couplings that we might be interested in QED and in gravity, they scale by 1 over root h. So it will turn out that we want to distinguish now between the wave numbers and the momenta. That will become important. So I'll introduce a notation for the wave numbers by borrowing the corresponding momentum. So if we look at what happens here, the net from putting in the h bars in an endpoint L loop amplitude in scalar QED scales as h bar to the 1 minus n over 2 minus L. That's right. It is, those are both minus signs. So those are powers of h bar in the denominator. So your first reaction might be to exclaim, oh no, it looks as though higher orders are out of control and that they're getting larger and larger as I take h bar smaller and smaller. But before we panic, we should realize that we've actually seen this before. And at least amplitudes people have. Because if you think about loop amplitudes in QCD, they are singular in the dimensional regulator epsilon. Everyone uses dimensional regularization. Epsilon is equal to d minus 4 quantity over 2. The amplitudes go as g over epsilon to the 2L, 2 powers of epsilon and 2 powers of the coupling g per loop order. And so when we take epsilon to 0, then it looks as though higher orders are again out of control. But as we all know, or at least the amplitudes people all know, then that is wrong. They are not out of control because these singularities are canceled by real emission contributions, and that happens when we consider physical observables. And indeed, the same thing is true in our classical limit, the limits that we're interested in. There are going to be other factors of h bar as well. So the behavior of amplitudes is not the whole story. We have to think about observables. Indeed, in general, if one is doing a calculation and there's a singularity that appears, then it's a signal that either the quantity that's being calculated is not truly physical. That might be the example of a virtual loop amplitude, or there are missing contributions, as in the case of the missing real emission contributions. So with that kind of admonition, let's go ahead and look at some physical observables. So the first thing we'll look at is that of the outgoing momentum. And we can simply measure the momentum, which I'll denote here by a bold P. Other places I'll denote it by a blackboard P, in the outgoing state. Now we've prepared an incoming state that will ultimately, with appropriate choice of the wave function, be designed to give us a point particle, but we don't know what the outgoing state is. On the other hand, we have a physical theory and it gives us an S matrix. And here we want to think of the S matrix as being the evolution operator from the distant past to the distant future. So we can write the out state as the S matrix acting on the in state. So that allows us to write the final momentum in that form. And if we want to, we can put in a complete set of states and rewrite it. So we now have a phase space integral over R1 and R2, which here are the quote intermediate states, but in reality, you should be thinking of them as final state momentum. So that's how you have a connection to scattering amplitudes. You have some sort of integral over a square of the scattering amplitude. Okay, the impulse is just the change in this momentum. So we have to subtract the momentum measured in the initial state. That's easy enough. We just evaluate it in the initial state. And we now write the S matrix in terms of the forward part and the transition matrix, and use unitarity and then shake things up a little. And we can write our master formula for the impulse. There are two terms here, one which involves a single power of t and the other which involves 2 powers of t. And this is actually an expansion that holds to all orders in perturbation theory. Of course, we can expand it order by order. At the leading order, we'll just count contributions from the first term. At higher orders, we'll need both of the terms. It's helpful to look at this diagrammatically because it's a little bit of an exotic thing, for at least for amplitudes people. So there's an on-shell integral over the phase space, essentially of a term that's linear in a scattering amplitude. That corresponds to the first term. And then there's an on-shell integral and a sum over arbitrary number of additional emissions of something that's the square of an amplitude. And the filled in circle here indicates something that's to all orders in perturbation theory. Now, there are different momenta running around here. There's the incoming momenta, which are denoted here by P1 or by P1 plus Q, because these are 2 copies of the initial state. So from the point of view of the scattering amplitude, this looks like a momentum transfer, but in fact, it's really a mismatch between the 2 different copies of the incoming state. And if you want something that really is genuinely a momentum transfer, you should look here, and you'll see that the difference between the momenta here and the quote intermediate state from the operator point of view and the initial state, that is a momentum transfer, because these are really the final state momentum. So we can we still have all these singular looking powers of H bar running around, but we have to finish our analysis. And it's good to think a little bit about non-relativistic wave functions. And if we had a minimum uncertainty one, a Gaussian, the bold P here is just the spatial momentum, then it would involve a ratio in the denominator between the Compton wavelength and the kind of intrinsic spread of the wave function. And there's a dimensionless ratio, which I'll call C, which is controlling it. And one can build relativistic wave functions, which are controlled by the same parameter. You need an additional 4 momentum parameter to build some Lorentz invariant. And when you introduce that parameter, which I'll call U, it turns out that it ultimately has the interpretation of the 4 velocity. So you can actually build an exponential of the momentum dotted into what will ultimately be the 4 velocity and divided by this parameter C and by M to make the dimensions work out. So we have 3 scales in the problem. There's the Compton wavelength, the wave function spread, and the scattering length, which in the present calculation turns out to be of order the impact parameter. We need the particles to be localized, and that gives us 1 inequality. And we also want the wave packets to be well separated so that the particles are not peering into each other. These are supposed to be classical point particles at the end, after all. And you can do this analysis more carefully, and you find this, this set of 2 inequalities is what you need. So what does that mean concretely? I'm going to introduce this double angle bracket notation to indicate a certain set of operational procedures, which by this stage, you can pretty much turn the crank blindly. You don't have to be thinking about doing power counting inside of amplitudes or anything like that. We extract the H bars in the couplings. We extract the H bars in the messenger momenta. One of the aspects of imposing that set of inequalities is precisely that for massless momenta, you should be using wave numbers and integrating over wave numbers. And that produces a set of H bars which compensate the singular H bars. Now, there can still be individual contributions which are singular in H bar. So you may indeed need to Laurent expand in H bar, and this can lead to the appearance of derivatives of delta functions in various places, but that is correct. And in a physical observable, these singular terms will ultimately cancel. And finally, you're supposed to integrate over a massive phase space. And at the end of the day, you want to replace the massive particle momentum by its mass times its forward velocity. I'm not going to work through extended examples here, but I'm just going to outline how it works at leading order. So here, only the first term out of the two terms in the master formula for the impulse contributes. It's an expression of order g squared. And the hatched lines here indicate that we're only looking at the tree amplitude. So I've extracted various factors of h bar from the measure, from the delta functions, and from measuring the momentum difference, which is ultimately here represented by the the wave number mismatch. And then we have a tree level amplitude. And when we finally put it inside the double brackets, these wave function forms basically reduce to delta functions, and we end up with a very simple integral. It's just a tree level amplitude, one of the rare cases perhaps where it's just as easy to do Feynman diagrams. Incidentally, it's essentially the same integral here in QED as it would be in gravity. Very simple example of how it's only the factors, some kinematic factors arising from the amplitude that are different. And so it's a simple example of how double copy can help you. So here there's still an h bar out in front. There'll be a 1 over h bar squared. There'll be a 1 over h bar squared coming from the 1 over q bar squared in the scattering amplitude. And so of course we'll end up with something that is order h bar to the 0 and has a nice classical limit. One can do this at next to leading order. One can do it for gravity, but instead, I'm just going to jump straight to the gravity impulse at N and LO in a very thorough paper by the quartet I mentioned earlier, just earlier this month. So they did both in general relativity and in the n=8 supersymmetric supergravity theory, the order g cubed computation, which corresponds to a two-loop calculation, which I'm showing here, the virtual pieces. There are also emission diagrams that need to be taken into account. And in fact, with the technologies available, the main challenge they faced is that of integration, to reduce to master integrals, to then use the method of regions and split things into potential and radiative regions. And finally, they chose to split things into transverse and longitudinal parts. And fortunately, some of the formulae are simple enough that I could pick them out of their paper and display them on this transparency with the help of their functions that are listed here in the above. So they've split it into conservative and radiative, and to get the total impulse, you'd have to sum these two, and from that you could then extract the scattering angle. So that's what happens when one is interested in scattering of massive particles, and we'll come back to that at the end when we're also interested in radiation. But one can also ask the question, what about massless particles? So generically, we call the photons and gravitons, or massless particles, generally messengers. We can ask the question about what about messenger waves, because ultimately the classical limit of massless particles is some sort of a wave. So to describe that classical limit, we're going to use coherent states, and these are essentially exponentials of the creation operators weighted by what we call a coherent wave shape. The quantum optics people may have a different name for it. And this operator creates a coherent state, and this is one of the states out of which we will build our incoming state. And if you want a kind of quick picture of what this thing is, then appropriately rescaled. And of course, it has to be chosen so that appropriate rescaling has a proper classical limit. The alpha bar essentially gives you the Fourier coefficients of the classical field. Okay, we have to have a coherent state, but that's in itself not enough for classical behavior. We also have to require factorization of two field expectation values. And so, for example, that would be the factorization of the product of the photon field operator. And that can happen when h bar goes to 0. And it corresponds, in fact, to the number of photons becoming very large. And so that's, in a sense, a coherent state with a very large number of photons is what we're going to call a classical wave. So one of the classical things, classic, I should say, rather than classical, is of course the light deflection in general relativity, taking us back over a century. Now, unlike the case for massive particles, at least once you've chosen the spin of the massive particle, there would be kind of a unique, sensible classical limit. Here, there are actually many different kinds of waves that you could extract. And for this purpose here, we're going to choose alpha bar to represent a continuous and narrow beam. So we're going to be choosing it to be represented by a product of three Gaussians. So there's a transverse width and there's a longitudinal width. And it's basically narrow centered around some particular wave number. So it's very close to monochromatic, and then it has a small dispersion. So it is spreading, but it's spreading very little. And ultimately, the idea is that we want to try and get a result which would be in the geometric optics limit. So if we think about the inverse of these spreads, these would be things of dimension of length now. So there's a perpendicular size and a longitudinal size. And we also, of course, have the wavelength of our beam of light. And we want this relationship to hold. We want to be working in the limit where the wavelength is certainly much smaller than the transverse size, and again, much smaller than the longitudinal size. And it is possible to find classical configurations, of course, that violate this, but we're not going to be using them right here. So we're going to go ahead and build an initial state. Again, we're going to build now not just plane wave states, but a product of a plane wave state for the massive particle and for the coherent state. So that's going to be our basic two particle incoming state. And again, we're going to weight it by a wave function for the massive particle. We're going to be considering here scattering of a photon off of a neutral massive particle, gravitational scattering. And again, there's going to be an impact parameter which is encoded in the phase, and we have an integral over the phase space of the massive particle. So we use the same formula for the impulse that was given earlier. And again, at leading order, only the first term contributes. Of course, higher order, you need to include both of those terms. And within the coherent state, mostly because of the structure of the gravitational scattering amplitudes, only the single photon states contribute. And one can go through the analysis of the classical limit. One finds, again, that it is the wave numbers for the momentum mismatch, the wave numbers for any final state additional radiation, and the wave numbers for massless loop momenta that are relevant. And this is coming from constraints that are relating also to the Gaussians for the beam structure. And one can turn through the crank again, and there's a very similar formula that emerges to the formula, the leading order formula for the impulse, except that here there is a dependence on the type of classical wave in a so-called beam function, which I've left in here. And from the impulse, we can obtain the angle. And if we go to the small angle limit, then we obtain the well-known result of 4gm over b. Now, the observables we've been talking about up to now are, in a sense, global observables. So I didn't talk about radiation, but we could evaluate the total momentum in the final state and derive formulas that you can look up in our paper if you're curious. And in a sense, the momentum change is also an integral over the entire phase space. What we're interested in ultimately in the LIGO or context, or in general in the context of observing gravitational waves, are what one might call local observables. There's some radiation that propagates, and we have a scattering region in the same sort of spirit that Ashok Sen talked about. And then there's some scattering process, and then there's some merger process, and then there's some radiation that propagates in some direction, and then we have an observer that's looking at that radiation either directly or using phototubes or using very sophisticated gravitational wave detectors. So in that scattering region, we have, in a sense, a current that is generated, and the number of indices it's carrying depends on the nature of the interaction. It might be none for a scalar, 1 for a vector, and 2 for tensor or gravity. And so we now can look at some local radiation observable as a function of now space-time x, and we can propagate it from that scattering region. And when we do that, the thing that we're ultimately interested in is the large distance behavior that's suppressed by single power of x. There are additional terms that are suppressed by higher powers of x. And its coefficient is what we're interested in, is the waveform. So that waveform is given by a Fourier transform of this object, and there's both a clock time and the coordinate time, but the absolute phase is of course not observable. On the other hand, the relative phase, for example, between different observers is observable, and that's one thing that we would like to be able to keep, something that we can't do if we just measure the total emitted momentum. So the way one wants to go about doing that is, in the case of QED, to measure the actual field strength at some distance observers. So now we're going to go back to look at the scattering of two massive charged point particles and look at the measurement of the actual field, the electric field. Correspondingly, we would, in gravity, we'd look at the scattering of two massive neutral particles and look at the expectation value of the Riemann tensor. And again, the outgoing states we can write in terms of the S matrix acting on the incoming states. And again, writing out the S matrix and using unitarity, we come up with a formula which is very reminiscent of the formula for the impulse. And again, there are two terms. This is an all orders formula. And at the lowest order, which is here, G cubed, or of the T matrix, and at higher orders, we will also have contributions that involve two powers of the T matrix, which start at order G to the fifth. And again, there's a similar expression for the, it's similar in its structure to the expression for the impulse delta P. So we can plug this into, we have our incoming waveform, and we integrate over the phase space for the right hand copy and also for the conjugate copy of the incoming wave state. And we now also have an integration over the radiated momentum that's sitting inside the F operator. And when one works out the matrix elements of the transition matrix, then at the leading order, not too surprisingly, one comes out with scattering amplitudes. And these scattering amplitudes here are exactly 5-point amplitudes at lowest order. And there's a phase space integral over them. Now, I'm not going to have time to review that part of the original paper, but essentially the integration over the massive particle phase space of the scattering amplitude appropriately decorated essentially gives you what we call the classical radiation kernel. Here, the waveform is essentially just the integral over the photon phase space of that kernel. So we can go back and forth from our waveform to the spectral function. And the message here is that in fact, this long path has a shortcut that it's the classical radiation kernel is basically the spectral function. And as we just saw on the previous transparency, that classical radiation kernel up to an integral is basically the 5-point amplitude. One can go ahead and compute it in QED. I won't take you through the details of the computation. And one obtains an answer that here we've expressed as all good amplitudes people do in a spinor language. And there's also a set of Bessel functions. In fact, some of the terminology is a refugee from 19th century mathematics. These are Bessel functions, modified Bessel functions of the second kind. And they are the start of another tower of interesting functions that are kind of analogs to the loop integral functions, the polylogarithms that we know and love. And I'm sure that there's a lot that can be said about their general properties and symbology that we will be probably discussing in years to come. So I see that in spite of actually having a large number of slides, I've actually managed to not annoy the chairman and or the colloquium speaker and run too late. So I'll come to my summary here that the double copy, and I think as we continue doing more explicit calculations, other structural features will offer a simpler avenue to calculations of gravitational wave observables from scattering amplitudes. And the path that we've taken is to study observables that are valid in both the quantum and classical theories, and to organize the formalism to take the limit in a simple way. So in a sense, we have to do some hard thinking initially to organize the calculation, but once we have our master formula for the desired observable, one can turn the crank. Now, as Enrico, Julio, Michèle, and Mao know, this is not necessarily a simple thing, but at least you can focus on that core aspect of the calculation without having to think about how to look for contributions inside amplitudes and so on and so forth. So one needs to count the bars and then use momenta from massive particles to classical waves into this pictures using coherent states. One can also show, for example, that the radiation, outgoing radiation that's emitted also takes the form of a coherent state, at least to lowest order. And the waveforms emerge very directly from measuring the electromagnetic field in the QED case. Of course, there are lots of challenges. We're going to need explicit calculations and understanding how to transfer these ideas of waveforms to bound state calculations. Thank you.
Thank you, David, for a very nice talk. I'm sure by some questions. Just speak up and unmute yourself if you have a question. Might be missing you. If not, maybe let me. Oh, there's one. Chache.
Hi, David. Thanks for a nice talk. So I just wonder for your
Hi,
the waveform. Hey, so the waveform you write as the 5-point amplitude. For the 5-point amplitude, if you count the H bar, I believe it's not just leading order in H bar because you have the part coming from the soft emission. So can you comment on how you treat that part of the soft emission in your 5-point amplitude?
So at leading order, I may not be quite answering the question that you have in mind, but let me give an answer and then you can iterate. So at leading order, there's no issue of having to worry about any IR divergences. I mean, the emission that's there is what you detect. When you go to higher order, then there will be soft singularities inside the loop contributions. There will be additional soft singularities arising from phase space integrals. And those actually will cancel not only powers of epsilon, but in general will be necessary for cancellation of singularities in H bar. And I don't expect there will be anything unusual that happens except for the consequent appearance of various derivatives of delta functions and things like that.
Maybe I should clarify my question. I think what I'm asking is, so from your 5-point amplitude, you have the part that you have like emission from initial or final state. And those diagrams that have like additional matter propagators, so you'll get enhanced in H bar counting. Of course, like if you add all the diagram, if you ignore the I epsilon, that add up to 0. But if you keep the I epsilon, then those will give you delta functions in the immediate energy. So it won't affect finite energy graph down, but those will affect the 0 energy piece.
Are you asking here about whether there's traces of memory effects or the other long distance contributions that Ashok was talking about?
It is related to memory effect, yes.
Okay, so the short answer is we haven't really looked at that, but my suspicion is that in the leading order calculation here, this is not something we're going to be able to see. We would need to go to higher order to be able to see that.
Okay, thanks.
Okay, the next one is Dimitris, I believe.
Yeah, hi. I had a question about the factorization property of the photon operator. Do you expect subleading terms to be important when you go to higher orders?
So no, these are terms which are the correlation effects. I'm not sure if that's really the right quantum optics word for it, terminology for it, but those correlation effects are suppressed in H bar. So I don't have an application in mind, but if you were potentially interested, or I don't know, maybe someday if my colleagues Josef Benna and Nick Warner turn out to be right and the quantum effects in these supermassive black holes are actually on the scale of the Schwarzschild radius rather than h bar times the Schwarzschild radius, and you wanted to carry out this calculation to kind of beyond the classical order, then you would have to worry about them. And then this formalism in principle would allow you to incorporate effects that are kind of the next corrections, first quantum corrections beyond classics. But in the classical limit that we're interested in, at any order in perturbation.
So there's no h bar over h bar possibility for, like, it's clear that there's never going to be h bar over h bar.
David?
I'm sorry, I think I was, my Zoom decided for whatever reason to reconnect. So I don't know if the last part of my answer was swallowed or not. Did it all come through, Dimitris?
So I heard you say that there's never that it's gonna be quantum at any order in perturbation theory.
Yes.
That was the last thing I heard. I was just wondering, why is there never gonna be h bar over h bar? So you have extra propagators, there's extra h bar in the denominator, and then you need to keep an extra h bar in that relation to be certain.
Well, I don't have a proof of that, but just as I don't have a proof, in fact, that that singular terms, I mean, there's not yet any analog of the KLM theorem that says that singular terms absolutely will cancel, but I think the structure of contributions is such that they are probably always going to be suppressed in h bar. And that's actually something one can probably think about more simply than an analog of KLM for h bar.
Okay, yeah, thanks.
Okay, the last question is for Alex Ochirov.
Hello, thanks for the nice talk, David. I'd like to ask about the last slide, the penultimate slide that's no longer on the screen. Well, nothing is, I'm not seeing any,
right.
but the one that's showing the leading order.
Let me try and share it again. I think when my Zoom connection died, it also unshared the screen.
Right, yeah. So the first thing is there a typo in the second term? Because the second term looks almost exactly like the first, with 1 going to 2, except for the mass.
It's possible.
Yeah, okay. Well, a more interesting question is there any hope, do you have any hope that the bound state analog of this could be obtained by some analytic continuation? Is there, like, if...
Okay, so first of all, the second term is, yeah, the second term is related to the first by an exchange of U1 and U2. So I'm not sure why you're saying it's exactly the same, but
well,
in any
also
event,
Q1 goes to Q2, so I was thinking that maybe M1.
I mean, these are two different, charges, right? But also U1 goes to U2. That's a very interesting question, and I don't really have anything to report on that today, but it's certainly something that we want to think about. Is there some souped up version of what Rafael showed us earlier that can be used as a shortcut to analytically continue this to to bound state observables. That would be a great thing, but I don't know how to do that today.
Do you know how this thing looks like? If this can be drawn as a shape, as a sample shape?
Yeah. In fact, if it were happened to be in audio frequencies and you had a sequence of scatterings, it sounds a little bit like a machine gun. If you have a long sequence of these scatterings, it sounds a little bit like a machine gun.
Oh, a machine gun.
Yes.
So like a shot. One is.
Yeah, each one is a shot. Yeah, that's what it sounds like.
So yeah, nothing like a chirp, but maybe if there is a deformation after all that goes that transforms the shot into a chirp.
Maybe.
Okay.
I mean, I think it will be interesting to both to compute this to higher order and you know, potentially even hunt for these things inside the LIGO stream. I don't know if that's realistic or not. So.
Thanks a lot.
Okay, the last question from me. You don't have that result for gravity yet, though.
No, it's at least in the form that we have it, which may not be the simplest form. It involves kind of non-classical Bessel functions, and so we have not we have not completed it. Let's put it that way.
Okay, so let's thank David once more for a very nice talk, and also Michèle for the talk before. And close the session. I also want to advertise the colloquium, which is actually starting now on a different channel. So see you all tomorrow. Bye.
Bye-bye.